Out there, beyond the gleam of familiar constellations, beyond the reach of ordinary starlight, beyond even the most imaginative depictions of galaxies, there lies a phantom. A ghost. A giant so vast, so eerily transparent, and so impossibly faint that it evaded detection for most of modern astronomical history. Imagine a spiral galaxy so diffuse that light itself seems reluctant to escape from it, a galactic titan whose arms stretch farther than any other spiral we've ever observed. And yet, when you look toward its coordinates in the sky, there is almost nothing. No brilliant blaze like Andromeda. No sweeping arcs like the Whirlpool Galaxy. Just darkness. Emptiness. Or so it seems. But that's the trick the universe sometimes plays, hiding its most colossal structures in plain sight. This is the story of Malin 1, a galaxy so unique that it doesn't just stretch our understanding of cosmic proportions, it stretches our very idea of what a galaxy even is. Nearly invisible, impossibly huge, and shrouded in dark matter, Malin 1 isn't just a record breaker, it's an enigma. A silent giant drifting at the edge of comprehension, defying the rules written by brighter galaxies. But before we continue, subscribe to the channel so you don't miss out on any of these videos. In the vast night sky, filled with luminous spirals and vibrant clusters, Malin 1 is an outlier, so dim that it took the right eyes, the right tools, and a touch of serendipity to find it at all. And even once found, it continued to elude full understanding, like a shadow dancing at the edge of a campfire. Its spiraling arms stretch out 6 times farther than the Milky Way's, but glow with such a faint whisper that even our most powerful telescopes struggle to capture them. A galactic illusion. A whispered memory of cosmic evolution. An enormous ghost suspended in the dark. What is this giant, and why does it matter? Because Malin 1 forces us to reevaluate our assumptions about how galaxies form, grow, and even hide. Because it suggests we may be missing a major part of the universe, not because it's beyond our telescopes, but because it's beyond our expectations. Because if Malin 1 can exist, undetected, for so long, perhaps the universe is far more full of such ghostly giants than we ever imagined. And perhaps our night sky is not merely punctuated by light, but haunted by invisible colossi. Let us now descend into the silence and shadow of Malin 1, to uncover the full story of this cosmic phantom. From its accidental discovery to its role in redefining galaxy classification, this journey will take us through the limits of visibility, the mysteries of dark matter, and the tantalizing thought that the night sky may be hiding more than it reveals. Let's dive into the cold, quiet vastness of the unknown, and meet a titan born of faintness, slowness, and space itself. Malin 1 is not your ordinary galaxy. In fact, it stands as the very definition of extraordinary, a cosmic outlier that challenges everything we thought we knew about how galaxies are built and what they're supposed to look like. At its core, Malin 1 is classified as a low-surface brightness spiral galaxy, or LSB galaxy. But even that designation doesn't do it full justice. It's not just any LSB galaxy. It is the largest spiral galaxy ever observed, with dimensions that boggle the mind and a structure so faint that, for most of human history, we didn't even know it was there. To understand Malin 1, we need to first unpack the concept of surface brightness. It refers not to the total brightness of an object, but to how spread out that light is over the area it occupies. A low-surface brightness galaxy emits light so diffusely that even if it has a lot of stars, they are spread thinly over a huge area. As a result, the galaxy appears incredibly faint, nearly invisible against the background darkness of space. It's not that Malin 1 is intrinsically dim, it's that its light is diluted across a canvas hundreds of thousands of light-years wide. The stars are there, the structure is there, but they shimmer like ghostly outlines, faint traces of light lost in the abyss. Yet, what makes Malin 1 even more remarkable is its classification as a spiral galaxy. We usually associate spiral galaxies with bright, elegant structures like the Milky Way or Andromeda, with well-defined arms, bustling star formation regions, and visible dust lanes. Malin 1 does have spiral arms, but they are so spread out, so ethereal, and so sparsely populated with stars that they're nearly impossible to detect without the right instruments, and long exposure times. It's like seeing the skeletal remains of a whirlpool in space, a ghost spiral turning in slow motion. What we do see, once the image is processed correctly, is awe-inspiring. A bright central bulge, small but comparatively intense, surrounded by vast, diffuse spiral arms that stretch outward for over 650,000 light-years. That's over 6 times the diameter of the Milky Way. For context, if the Milky Way were a compact city, Malin 1 would be a sprawling megapolis whose outer suburbs are barely lit. It's like comparing a flashlight to a low-watt bulb inside a massive fog. This immense scale and faintness means that Malin 1 doesn't show up easily in traditional telescopic surveys. It takes long exposures and image enhancement techniques to even begin seeing its outer disk. For a long time, astronomers thought its bright inner bulge was the entire galaxy. Only with deep imaging did the truth begin to emerge, a wispy halo of starlight far larger and dimmer than anyone had imagined. The structure of Malin 1 invites more questions than answers. Why does it have such a massive disk yet remain so dim? How did it form spiral arms without the intense star formation activity we see in typical spiral galaxies? And most tantalizingly, how many more galaxies like it are out there, hiding just beneath the surface of our observations? Malin 1 is also an object of theoretical importance. It challenges traditional models of galaxy formation, which are built around interactions, collisions, and the accretion of smaller systems. But Malin 1 seems like a galaxy that formed differently, quieter, slower, and with a vastly different star-making history. It stands as a reminder that the universe doesn't always follow the rules we expect. In the catalog of known galaxies, Malin 1 doesn't just stand out, it looms. A titan not by virtue of its luminosity, but because of its sheer scale and mystery. It's an entity that forces astronomers to consider the possibility that the cosmos may be more subtle and shadowy than our eyes can perceive. In the end, Malin 1's basic identity can be boiled down to this: a record-breaking spiral galaxy, impossibly large, almost invisible, and made mostly of things we cannot see. And it is only the beginning of what such galaxies may teach us. The story of Malin 1's discovery begins not with the click of a modern digital telescope, but with a photograph, more precisely, a photographic plate. It was 1986, a time when astronomy was still transitioning from traditional photographic methods to electronic detectors like CCDs. In this in-between era, many of the universe's secrets were still buried in these old photographic plates, waiting to be uncovered by those with the patience and skill to coax out their faintest details. One such individual was David Malin, an astronomer and photographic specialist working at the Anglo-Australian Observatory. David Malin wasn't just a scientist. He was also a master of image processing, someone who saw more than just stars in a photograph. He saw potential. His deep understanding of how to chemically and optically enhance photographic plates gave him a unique advantage. While most observers would stop at what the human eye could directly perceive on a developed plate, Malin delved deeper. He pioneered techniques to push the visibility of faint astronomical structures well beyond conventional limits. His work was particularly focused on revealing low surface brightness features, like faint nebulae, halos, and unbeknownst to him at the time, gigantic ghost galaxies. It was during one of these enhancement sessions that Malin noticed something strange in a photographic plate taken at the UK Schmidt telescope in Australia. The plate showed what initially appeared to be a typical elliptical galaxy, bright, compact, and fairly unremarkable. But when Malin began applying his advanced image processing techniques, slowly bringing out the dimmer parts of the plate using contrast adjustments and chemical enhancement, a colossal halo began to emerge around the bright core. At first glance, it seemed almost like a photographic artifact, a trick of the chemicals or some scattering of light. But the structure persisted, revealing a massive, diffuse disk surrounding the small bright bulge. It wasn't an illusion. It was real. And it was enormous. What Malin had uncovered was something previously hidden beneath the thresholds of standard detection. A vast spiral galaxy with an extremely faint disk extending far beyond what had ever been seen in similar structures. The galaxy's central region had misled observers into thinking it was just a compact elliptical. But Malin's enhancements peeled back the darkness, showing that this object was no ordinary galaxy. It was a behemoth, lurking in the shadows. This was not just an exciting find, it was revolutionary. Malin 1, as it would later be named in honor of its discoverer, instantly broke the record for the largest known spiral galaxy. Its discovery was published in 1987, and the astronomical community was stunned. How could something so enormous have escaped detection for so long? And more importantly, what did it mean for our broader understanding of galactic populations? David Malin's discovery wasn't just about unveiling a single galaxy. It cracked open an entirely new frontier in extragalactic astronomy. It hinted that the sky might be filled with other similarly massive, faint structures that had eluded detection simply because we weren't looking hard, or cleverly, enough. It raised the possibility that our census of galaxies was incomplete, biased toward those with high surface brightness and easy visibility. Malin's meticulous work with photographic plates demonstrated that the universe had been quietly hiding its most colossal structures in plain sight, veiled by the very methods we use to study it. His techniques brought not only scientific insight but a certain artistic touch to astronomy, blending chemistry, optics, and patience into a process that revealed cosmic ghosts invisible to standard observation. Today, Malin 1 stands as a testament to both the persistence of its discoverer and the profound idea that the universe's largest structures might not be the brightest, but rather, the most subtle. They require a different kind of observation, a different way of seeing. And in 1986, David Malin gave the world exactly that. The haunting mystery of Malin 1 lies not just in its size or faintness, but in the sheer fact that it went unnoticed for so long. A galaxy so vast, spanning over 650,000 light-years, should have been screaming from the sky. But instead it whispered. It whispered so softly that the combined force of decades of traditional sky surveys failed to catch it. And therein lies one of the most fascinating parts of its story. Malin 1 was hidden in plain sight, a ghostly monolith cloaked not by distance or obscuration, but by the limitations of our own perception and methodology. To understand how something so colossal remained invisible, we need to step back into the history of sky surveys and how astronomers traditionally catalogued galaxies. For much of the 20th century, the foundation of observational astronomy rested on photographic plates. These plates were exposed to starlight over long durations, capturing static snapshots of the heavens. They were marvelous tools in their time, responsible for a great number of discoveries, from quasars to distant clusters. But they had a key limitation: dynamic range and contrast sensitivity. Photographic emulsions, while excellent at picking up point sources like stars and the bright cores of galaxies, struggled to detect extended objects with low surface brightness. That is, even if a galaxy contained a lot of stars and was physically huge, if its light was spread too thinly over a wide area, the plate would not register it clearly. Instead, only the bright central bulge, if one existed, would be noticeable. Everything else would simply fade into the background fog of sky glow, chemical noise, and emulsion grain. In the case of Malin 1, its compact core did indeed show up on various surveys, but it was easily misclassified as a small elliptical galaxy, a common, unremarkable type with a concentrated light profile and no apparent spiral structure. Its outer disk, the part that gives Malin 1 its stunning scale and identity as a spiral galaxy, was too faint and diffuse to be picked up by standard observational techniques. For all practical purposes, Malin 1 was categorized and catalogued, but not truly seen. Add to that the fact that most early sky surveys were optimized for identifying bright objects. Surveys like the Palomar Observatory Sky Survey (POSS) prioritized detection of stars, nebulae, and galaxies that stood out clearly against the sky. The methods were inherently biased toward high surface brightness galaxies, those that emit a lot of light per unit area. That meant that an entire class of galaxies, the low surface brightness (LSB) galaxies, was effectively hidden from view unless someone knew exactly how and where to look, and how to look differently. This observational bias had massive implications. It meant that the cosmic census was skewed. Astronomers were counting the bright and ignoring the faint, creating a picture of the universe that favored what shined the most, not what existed in the greatest abundance or variety. Malin 1 was the most extreme case of this bias. Its discovery required not just better data, but a fundamentally different approach to how that data was analyzed. David Malin's technique of image enhancement revealed what traditional photographic analysis couldn't: the sprawling, gossamer-like arms of a galaxy so faint they barely existed above the background noise. His chemical and photographic innovations allowed for an increase in contrast without distorting the structural truth of the image. Where others saw a dot, he uncovered a colossus. It was like looking at a faded map under ultraviolet light. Suddenly, invisible ink begins to glow. But even beyond photographic plates, traditional telescopes had their own limitations. Optical instruments, those relying on visible light, struggle with objects that lack bright emission. Malin 1, with its ultra-faint arms and absence of intense star-forming regions, emitted little light in the bands most telescopes were tuned to. It wasn't a glowing furnace of starbirth like the Whirlpool Galaxy, or a radiant maelstrom like M82. It was cold, quiet, and slow. The light it did emit was stretched thin across a canvas so wide that any one section of it seemed almost indistinguishable from empty space. This issue is compounded when considering background noise. The night sky is not a perfectly black backdrop. Earth's atmosphere, cosmic rays, and scattered light all contribute to a subtle fog of illumination. For astronomers hunting faint galaxies, this glow acts like static on a radio, drowning out the softest signals. Malin 1's outer regions fall perilously close to this background threshold, meaning it could be, and often was, filtered out as noise. Another aspect to consider is that many surveys operate under exposure time constraints. Telescope time is precious, and most surveys are designed for breadth, not depth. That means shorter exposures are taken of many parts of the sky to cover large areas. While this strategy is efficient for detecting bright galaxies and other high-emission phenomena, it's inadequate for unmasking ultra-diffuse structures. Malin 1 required long exposures and deliberate effort, not the kind of thing that shows up in a cursory glance or a wide-field survey snapshot. Moreover, computational techniques used in automated galaxy detection further contributed to Malin 1's invisibility. Modern sky surveys often rely on software algorithms to identify and catalog objects. These algorithms are trained to look for specific shapes and brightness profiles, largely modeled on known galaxy types. LSB galaxies like Malin 1 fall outside those expected templates. In many cases, the software simply didn't recognize their faint outlines as galaxies at all. They were dismissed as background irregularities or imaging defects. Even today, despite knowing Malin 1's existence and location, capturing it in detail is an immense challenge. Its outer disk remains elusive even to powerful telescopes like Hubble. In many ways, Malin 1 still resists our gaze, still hiding in the twilight zone between presence and absence. It's a stark reminder of how much the universe can conceal when we only look in conventional ways. This is why Malin 1's discovery wasn't just a fluke, it was a turning point. It illuminated a blind spot in our methods. It forced astronomers to rethink their assumptions, not only about what's out there but about how we search for it. The realization that something so big, so significant, could go unnoticed for so long prompted a re-examination of data, a re-evaluation of detection thresholds, and an increased interest in the study of low-surface brightness galaxies. It opened the floodgates to a new understanding. The night sky isn't just dotted with light. It's drenched in hidden structures we've been overlooking for decades. So while Malin 1 floated in space for billions of years, minding its quiet business, it was only revealed to human eyes through persistence, ingenuity, and a willingness to see beyond the obvious. Its very invisibility was the lesson. What else, we now wonder, is hiding in plain sight? In the grand architecture of the cosmos, galaxies come in a stunning variety of forms: spirals, ellipticals, irregulars, dwarfs, giants. But even among this cosmic diversity, Malin 1 is something truly exceptional. Its very nature places it at the far end of the galactic spectrum, massive but nearly transparent, large yet ghostly, structured yet silent. Galaxies like Malin 1 are so rare that they can be counted almost on one hand, and their existence continues to puzzle astronomers. Why is Malin 1 so unusual, and why are there so few galaxies like it? To begin with, let's revisit the two primary characteristics that make Malin 1 stand out: its extraordinary size and its extremely low surface brightness. Both of these properties are rare on their own, but to find them in combination is almost unheard of. Massive galaxies, such as the Milky Way or Andromeda, usually exhibit high surface brightness regions, vibrant spiral arms filled with gas, dust, and active star formation. Their cores blaze brightly, their arms shine with young, hot stars, and their structures are often well-defined and easily visible even in distant sky surveys. These are the galaxies that dominate astronomical catalogs, not just because they're common, but because they're detectable. Low surface brightness galaxies, on the other hand, tend to be small and faint. Many of them are dwarf galaxies, small systems with little star formation, minimal gas content, and diffuse light profiles. While LSB galaxies are interesting in their own right, they are usually modest in scale. In contrast, Malin 1 is not only diffuse and faint, it is huge. It combines the enormous scale of a supergiant spiral with the ghost-like visibility of an ultra-diffuse object. This dual identity is precisely what makes it so rare. Why don't we see more galaxies like Malin 1? Part of the answer lies in the difficulty of detection, as discussed previously. But even beyond that, the formation and persistence of such galaxies appear to require a very narrow set of cosmic conditions. To build a galaxy that large without also igniting intense star formation, and thus without lighting up the arms with bright, young stars, means that something very different must have happened during its formation. In the conventional model of galaxy evolution, massive galaxies grow through hierarchical merging. Small systems collide and combine over time, triggering bursts of star formation as gas clouds are compressed. These mergers typically create bright, active galaxies. But if a galaxy were to form more passively, through slow accretion of gas and the gradual buildup of stars without major collisions, it might avoid the starburst events that lead to high surface brightness. It would grow large, but faintly. It would form quietly. It would, in effect, become a cosmic ghost. This is one of the leading theories behind Malin 1's rarity. It may be the product of quiet, isolation-based evolution. Without significant interactions or mergers, it never developed the dense, bright features of more familiar spirals. Its spiral arms are there, but they're ethereal, sparsely populated, and not currently producing stars at any notable rate. It's as if the galaxy began to form normally, then diverged into an entirely different path, one where size continued to grow, but luminosity didn't follow. Another factor is gas density and star formation efficiency. In typical galaxies, regions of high gas density collapse under gravity to form new stars. But in Malin 1, the gas appears to be spread so thin across such a vast disk that it never reaches the threshold needed to trigger large-scale star formation. It has the fuel. Immense reservoirs of hydrogen have been detected, but the conditions just aren't right to turn that gas into stars. And so the galaxy remains dark, dim, and quiet. There are a few other galaxies that show similar traits. Galaxies like UGC 1382, Dragonfly 44, and a handful of ultra-diffuse galaxies in the Coma cluster share some resemblance. Some are massive but faint, others are large but low in stellar density. Yet none approach Malin 1 in terms of sheer diameter or the scale of its faint spiral structure. It is truly in a class of its own, a lonely apex predator in the strange ecosystem of the ultra-diffuse. This rarity also has cosmological implications. If galaxies like Malin 1 are truly uncommon, it tells us something about the statistical distribution of galaxy types. It suggests that while LSB galaxies may be more common than we once believed, the subset of massive LSB spiral galaxies remains extremely limited. This could mean that the conditions required to form them are rare, or that their visibility window is short. That is, they don't remain in their faint, ghostly form forever. Perhaps Malin 1 represents a transitional phase or an evolutionary endpoint. Alternatively, their rarity may simply be observational bias in disguise. We still might be underestimating how many of these giants exist because we lack the technology, or techniques to find them. Some astronomers speculate that with the advent of more sensitive surveys and deep imaging telescopes, a new generation of Malin-like galaxies may emerge from the darkness. But for now, Malin 1 is the benchmark, the flagship of an elusive fleet, if such a fleet even exists. There is also a question of environment. Malin 1's location, far from galactic clusters and major interactions, may have preserved its delicate structure. In more populated regions of space, gravitational encounters tend to warp or disrupt galaxies, often triggering bursts of light-producing activity. Malin 1's isolation may be the very thing that allowed it to grow so large and stay so faint. And that combination, massive structure with minimal interaction, may be cosmically rare. In the end, Malin 1 is not just a rare object, it's a challenge to the standard model of galaxy formation. It stands like a quiet rebuttal to our assumptions, a softly glowing reminder that not all galaxies follow the bright, noisy path we've come to expect. While we continue to find galaxies at greater distances, with more exotic properties, none quite match the combination of scale and stealth found in Malin 1. It is, for now, the undisputed monarch of the low-surface brightness realm, a rare phenomenon in a universe that still has many secrets to give. Size in the universe is often a deceptive metric. We see brilliant galaxies like the Milky Way, Andromeda, or the Whirlpool Galaxy, and we assume their grandeur defines the upper limit of cosmic architecture. The Milky Way, our home, spans a breathtaking 100,000 light-years in diameter, its vast spiral arms wrapping around a central bulge teeming with stars, gas, and dust. It holds hundreds of billions of stars and countless planetary systems. To us, it feels massive because it is massive. But then Malin 1 steps into the frame, quiet and subdued, and completely redefines the scale. Not just a little larger. Over 6 times larger. At an estimated diameter of 650,000 light-years, Malin 1 isn't just bigger than the Milky Way, it absolutely dwarfs it. If you were to overlay the Milky Way on top of Malin 1, our galaxy would vanish entirely within its pale arms. In fact, you could fit the entire Milky Way 6 times across and still not reach the rim of Malin 1's ghostly disk. Its immense size is difficult to visualize because our minds simply aren't wired to comprehend cosmic proportions. But imagine this. If the Sun were a grain of sand and the Milky Way a disk the size of a football field, Malin 1 would be a stadium complex, with outlying parking lots fading into the dark. And yet, it doesn't look like it should be bigger than the Milky Way. That's the paradox of Malin 1. Its visual presence is weak. Its central bulge is compact and resembles a normal galaxy. But the outer disk is so faint that, for many years, astronomers believed that the small inner core was the entire galaxy. Only when enhanced images were created did they realize that this ordinary object was surrounded by an extraordinarily vast structure, a disk that extended outwards to a scale almost unimaginable. Where the Milky Way ends in a well-defined halo, Malin 1 continues, blending into the intergalactic void with an almost invisible touch. Its arms are not tightly wound like those of classical spirals. They are loose, ghost-like, barely distinguishable even with long exposure imaging. They extend outward into nothingness, fading into the cosmic background in such a way that they seem more like shadows than structures. But when measured carefully, when the full reach of the hydrogen gas is traced, when the faintest outlines are examined, the numbers begin to emerge. And those numbers are staggering. Malin 1's disk reaches far beyond the bright inner region, to distances where stars are so sparse that they may be separated by thousands of light-years. This extended region isn't just a hazy puff of gas. It contains real structure, a coherent spiral pattern that implies a galactic system maintaining its rotation and gravitational balance across an expanse larger than any other known spiral galaxy. But what's even more remarkable is not just the raw distance, but the mass-to-size ratio. Unlike high-surface brightness spirals that pack their mass more densely, Malin 1 spreads its material so thin that entire regions of the galaxy could go unnoticed if not for the movement of gas or the faintest flicker of starlight. It's as though the galaxy is performing a sleight of hand, hiding its enormity through subtlety, diffusing its presence until only the most sensitive instruments and patient astronomers can recognize it for what it is. Consider the implications for navigation. If a civilization lived near the center of Malin 1 and sent out a probe at the speed of light, it would take 325,000 years just to reach the outer edge of the disk. By comparison, in the Milky Way, that same journey would take just 50,000 years. The scale is mind-bending. Even at sublight travel speeds, reaching the galactic rim from the core would be a voyage across epochs. Time and space stretch differently in Malin 1, not because of relativity, but because of sheer, unrelenting distance. This immense size also leads to an interesting cosmic question: how does such a vast structure hold together? Gravity, of course, is the answer, but the visible matter in Malin 1 is far too sparse to account for the gravitational cohesion necessary to maintain spiral structure over such distances. This is one of the reasons Malin 1 is so significant to dark matter research. It implies a vast dark matter halo enveloping and binding the galaxy, an invisible skeleton that holds the fragile bones of the galaxy in shape. The outer arms of Malin 1 likely orbit the galactic center over incredibly long timescales. Where stars in the Milky Way make a full rotation every 200 to 250 million years, stars or gas clouds on the outskirts of Malin 1 might take several billion years to complete just one orbit. It's an astonishingly slow spin, one that gives the galaxy an almost eternal quality. It moves, but with the grace and patience of a drifting continent. In a universe of dynamic and often violent transformations, Malin 1 seems to have opted for glacial stillness. And this raises another question: how did it get so big? Typical spiral galaxies grow through mergers and accretion events, but those also tend to stir up star formation and increase surface brightness. For Malin 1 to grow so large without becoming bright and active, it must have had a uniquely tranquil evolutionary path. Either it slowly built up over eons from diffuse gas, or it formed under special conditions that allowed for enormous scale but suppressed the usual star-forming activity. This makes its size not just a record, but a clue, a critical piece in the puzzle of galactic formation. Its sheer dimensions also affect how we think about cosmic structure. Malin 1 forces us to reevaluate where the boundaries of a galaxy lie. When do a galaxy's outer arms become part of intergalactic space? When does diffuse gas cease to be part of a galactic disk and become something else entirely? With Malin 1, those boundaries are blurred, smeared out across hundreds of thousands of light years. In a way, its vastness is not just a feature, but a statement, a monument to what the universe can create when given enough time, space, and quiet. Malin 1 doesn't roar across the sky. It doesn't burst with the colorful light of star-forming regions or the brilliance of quasars. It stretches out, calmly, like a ghost giant reclining in the void. To say that it is bigger than the Milky Way is technically correct, but vastly understates its uniqueness. Malin 1 redefines what we mean by big. It is cosmic vastness distilled into a galaxy, an entity so large and so elusive that it almost escapes classification. It isn't just a galaxy that outscales ours. It's a structure that sits at the far edge of what we can currently imagine a spiral galaxy being. And perhaps, it is only the first of its kind to be noticed. When one hears the term spiral galaxy, the imagination typically conjures up dazzling swirls of light, well-defined arms brimming with clusters of stars, dust lanes, and the radiant glow of stellar nurseries. In every popular image, from textbooks to NASA posters, spiral galaxies are portrayed as luminous pinwheels floating majestically in the dark. The spiral structure, in these cases, is obvious, bold, bright, and unmistakable. But Malin 1 defies that expectation. Yes, it's a spiral galaxy, but it's a spiral that barely glows. Its arms do exist. They spiral gently outward from the small, bright core, forming the grand disk that spans over 650,000 light-years. But calling them arms may be misleading to those accustomed to the radiant structures of galaxies like Andromeda or the Whirlpool. Malin 1's arms are ghostly outlines, almost abstract impressions of a spiral form. To detect them, one doesn't simply peer through a telescope. You must study, enhance, extract. They are so faint that even modern, deep sky imaging systems struggle to capture them in detail. What Malin 1 lacks in visibility, it makes up for in mystery. So why do its arms glow so faintly? The answer lies in a complex web of interrelated factors: star formation, gas density, stellar population, and surface brightness. Typical spiral arms are lit up by young, massive stars, hot blue giants that blaze brightly for a short time. These stars form in regions where dense clouds of gas collapse under gravity. But in Malin 1, the gas across the spiral arms is incredibly diffuse. Its density is too low to trigger widespread star formation. Without a new generation of bright, short-lived stars, the arms remain dark. That doesn't mean the arms are empty. Observations reveal that the galaxy is rich in neutral hydrogen gas, indicating there's fuel available. But the conditions in these arms don't appear conducive to turning that gas into stars. The lack of compression, the absence of spiral density waves strong enough to bunch material together, it all contributes to an eerie stillness. The arms stretch on and on, but they glow like a dying ember rather than a roaring flame. In fact, even where stars do exist in the arms, they are mostly older, cooler, and redder stars. These stellar populations emit much less light in the visible spectrum. The result is a structure that's there, physically massive, gravitationally coherent, but optically elusive. It's like standing in a dimly lit fog and trying to trace the outline of a distant mountain. You know it's real. You can map it. But you can't see it in the way your instincts expect. And even if one tries to observe Malin 1 in other wavelengths, challenges remain. Its faint spiral arms emit little infrared or ultraviolet radiation because of the scarcity of young stars and dust. It doesn't light up in the infrared the way dusty, star-forming galaxies do. Nor does it flare in X-rays, which are typically associated with violent phenomena like black holes or hot gas. It is, in every way, a quiet galaxy, not just visually but physically. The spiral pattern itself raises another profound question: how does it remain stable? Spiral arms in galaxies are not permanent structures. They are typically the result of gravitational perturbations, known as density waves, that move through the disk and compress gas into arms. These processes are more pronounced in high-mass, high-brightness galaxies where density is sufficient to sustain such wave propagation. In Malin 1, the disk is so diffuse that maintaining spiral structure over such enormous distances, hundreds of thousands of light-years, seems almost paradoxical. Yet the arms persist. They may be faint, but they are there. Radio observations, particularly in the 21 centimeter band where neutral hydrogen gas reveals itself, have confirmed the structure. In fact, these radio maps often show more of Malin 1's structure than visible light images can. They reveal the slow, grand sweep of the arms, curving like whispers through intergalactic space. This unusual visibility profile hints at a possible disconnect between what we see and what actually exists. Traditional optical observations are like looking at the universe through a flashlight. We see what reflects the light back. But galaxies like Malin 1 exist in the shadows, largely invisible to those who rely solely on visible wavelengths. They are reminders that not all structure is bright, that in the vast canvas of the cosmos, shape and presence don't always equate to luminosity. The phrase, "a spiral that barely glows," might sound poetic, but it is also scientifically precise. Malin 1 is a spiral. It rotates. It has arms. It has a disk. But it glows so faintly that entire generations of astronomers overlooked it. The universe, in Malin 1's case, decided to build an architectural masterpiece out of stardust and silence, and then dim the lights to nearly nothing. The implications go far beyond aesthetics. If spiral structure can exist in such low luminosity regimes, then our understanding of galactic morphology must expand to include these nearly invisible giants. It suggests that the physical processes forming spiral arms can operate under a broader range of conditions than previously thought. It also raises an important observational warning. We may be missing an entire hidden population of ghost spirals, vast structures that simply don't shine brightly enough to be seen by conventional means. So Malin 1 glides through the cosmos not as a beacon, but as a shadow with form. Its spiral arms are like echoes from a distant time, unfurling across a scale that defies reason, yet refusing to shine. In a universe where light is often equated with importance, Malin 1 humbles us with its quiet vastness. It doesn't announce its presence. It barely even glows. But in doing so, it teaches us more about the diversity, subtlety, and depth of the cosmos than the brightest galaxy ever could. At the heart of Malin 1 lies a paradox, a contradiction so stark that it almost seems unreal. In the center of this vast, ghostly disk, this nearly invisible spiral that stretches farther than any other known galaxy, there's a small, bright, compact core. It glows with the familiar intensity of a normal galaxy, dense and luminous, packed with stars. This dense core is what originally fooled astronomers into thinking Malin 1 was just a run-of-the-mill elliptical galaxy. But as technology advanced and the surrounding haze was revealed, it became clear that this bright nucleus was merely the tip of an unimaginably large iceberg, surrounded by an extremely faint disk unlike anything we'd ever seen. This contrast between the inner and outer regions is one of the most startling features of Malin 1. It's like walking into a room and seeing a brightly lit candle in the middle of a vast, nearly dark hall. Your eyes are drawn to the flame, and unless you adjust your vision, or enhance the image, you never know that the darkness hides the walls, furniture, or architecture sprawling far beyond. The central bulge of Malin 1 is that candle. It appears compact, structured, and recognizable. But beyond that lies a faint, gossamer-like spiral disk that is so diffuse it borders on invisible. The central bulge itself resembles those seen in typical spiral galaxies. It's likely composed of older, metal-rich stars and possibly contains a supermassive black hole at its core, though the evidence is still unclear due to observational limitations. This region emits sufficient light to stand out in optical surveys. It's what got noticed first. Its compactness and brightness are what initially led to Malin 1 being misclassified. There's structure, density, and heat, qualities that astronomers can recognize and measure with confidence. But this core sits in almost complete visual isolation from its surroundings. There is no gradual fall-off in brightness like we see in most spirals, where the arms taper off in a smooth gradient. Instead, there is a stark drop in light. The moment you move away from the core, the intensity plummets. The disk is there, but you have to work to find it. The contrast is not subtle, it's dramatic. The brightness ratio between the inner bulge and the faintest detectable regions of the outer disk is so extreme that it practically ensures invisibility unless enhanced or captured under very specific imaging conditions. This stark dichotomy raises some fundamental questions about how such a galaxy could have formed. In normal spiral galaxies, the bulge and disk evolve somewhat in tandem, shaped by mergers, interactions, and the rate of star formation. The disk is usually teeming with young stars, gas, and bright stellar nurseries. But in Malin 1, the core seems to have followed a different path than the rest of the galaxy. One possible explanation is that the central bulge is the original component, formed early in the galaxy's history during a rapid collapse of material. It may have experienced a burst of star formation billions of years ago, becoming dense and luminous. Then, over time, the galaxy may have slowly and quietly accreted additional gas and material from its surroundings, forming the massive outer disk. But because this accretion happened so gradually, and in an environment with few gravitational interactions to compress the gas, the resulting disk remained incredibly diffuse, with little new star formation to brighten it. Another possibility is that Malin 1 is the aftermath of a failed merger, or an aborted collision. Perhaps a galaxy merger occurred in the distant past that contributed to the bright core, while the outer material settled into a vast, tenuous disk that never fully ignited. Or perhaps there were no mergers at all, and this is a truly pristine structure, something that formed uniquely from the early conditions of the universe in a low-density region of space, allowing it to evolve without the violent interactions that shape most galaxies. Yet another hypothesis points to the separation of mass components. The core could be stellar mass-dominated, while the outer disk is primarily made up of dark matter and hydrogen gas, with only a sparse sprinkling of stars. If true, this would support the idea that Malin 1's disk is not just faint because of low stellar density, but because much of its mass is invisible, with only minimal starlight managing to peek through the veil. The contrast also challenges our observational methods. Many galaxy classification systems rely heavily on surface brightness profiles, plots of light intensity, as you move outward from a galaxy's center. Malin 1 breaks those curves. It doesn't decay in a neat, predictable way. Instead, there's a sharp drop, followed by a barely perceptible plateau that extends far into the cosmic dark. Detecting and modeling such profiles requires long exposures, advanced processing, and in some cases, the use of radio telescopes to detect neutral hydrogen that outlines the shape of the disk more effectively than light ever could. What this tells us is that Malin 1 is not just one galaxy with an unusual brightness profile. It may be a hybrid structure, with its core behaving like a conventional galaxy, and its disk belonging to an entirely different regime of cosmic architecture. The disk may have more in common with ultra-diffuse galaxies or even with dark galaxies, theoretical objects composed almost entirely of dark matter with little to no visible matter, than it does with the majestic spirals we know so well. This profound disjunction between the dense core and the faint disk leads to yet another critical point. We may have already catalogued many more galaxies like Malin 1, but misclassified them because only their cores are visible. In survey data, thousands of galaxies may appear as simple ellipticals, when in reality, they are surrounded by enormous faint disks that we simply haven't noticed. The core disk contrast effectively hides them in plain sight, making Malin 1 not only a rare object, but a possible representative of an entire hidden population. It's a reminder that visibility is not truth. What shines is not always what dominates. The bright, dense core of Malin 1 gets our attention, but the real story, the vast, ghostly spiral wrapping around it, is told in whispers, in shadows, and in stretches of faint starlight that require our deepest tools to hear. In that way, Malin 1 is a cosmic metaphor, brilliance in the center, obscurity on the edges, and mystery everywhere in between. A galactic illusion with a glowing heart, encased in near silence. It's not just a dense core and a faint disk, it's a paradox carved in starlight and dark matter. To truly appreciate the rarity and majesty of Malin 1, one must understand what it means to be a galaxy with low surface brightness, or an LSB galaxy. In the realm of observational astronomy, brightness is not merely about how much total light a galaxy emits, it's about how concentrated that light is. A galaxy can contain billions of stars and stretch across vast regions of space. But if that light is spread too thinly, the object can vanish into the cosmic background. That's the hallmark of an LSB galaxy. And among them all, Malin 1 reigns supreme. It is not just an LSB galaxy, it is the LSB galaxy. The biggest. The faintest at its scale. The king of cosmic shadows. So what defines a low surface brightness galaxy? The formal definition is deceptively simple. Any galaxy whose average surface brightness is fainter than 23 magnitudes per square arc-second in the B band, a blue portion of the visible spectrum. In simpler terms, that means the amount of light falling on a given patch of sky is lower than a threshold that the human eye, or even many telescopes, can detect easily. While high surface brightness galaxies like the Milky Way blaze with clearly visible structure, LSB galaxies seem to hover at the edge of visibility, like distant ghosts barely distinguishable from the blackness of space itself. This is not just a trick of distance. Many LSB galaxies are relatively nearby but still go undetected because they're so faint across their extended structures. In contrast, high surface brightness galaxies, even when small, light up the night sky with tightly packed star-forming regions, luminous arms, and vibrant cores. They are easy to find, easy to catalog, and easy to study. LSB galaxies, however, require a different kind of seeing, long exposures, contrast enhancement, and a deliberate search for what doesn't immediately announce itself. Malin 1 pushes the LSB concept to its extreme. It's not just low surface brightness, it has one of the lowest surface brightnesses ever measured in a spiral galaxy of this size. Some of its outer regions are as faint as 26 to 28 magnitudes per square arc-second, making them effectively invisible to the naked eye and undetectable in traditional astronomical imaging without extensive data processing. That means Malin 1 spiral arms emit less light per square unit of sky than the glow of the night sky itself. Let that sink in. The galaxy is fainter than the ambient glow of the universe. This ultra-low brightness is not due to a lack of content. Malin 1 is incredibly massive. Its total mass is estimated to be over 1 trillion solar masses, possibly more. That puts it in the same league as the largest galaxies ever known. But its mass is spread across such a gigantic volume that the average density is incredibly low. It's a bit like comparing a dense city to a sprawling, empty countryside. The latter may cover more ground, but you won't see its lights from afar. What makes Malin 1 truly special is that it combines size, mass, and structure with a surface brightness so low that it essentially evades standard methods of detection. Most LSB galaxies are irregular, amorphous, or dwarf in scale, quiet, underdeveloped systems lacking in both size and coherence. Malin 1, on the other hand, is a fully structured spiral galaxy, with arms, a bulge, and a vast disk. It is elegantly organized despite being almost invisibly dim. This makes it an important exception in galactic taxonomy. Prior to its discovery, LSB galaxies were not thought to come in such large and ordered forms. Malin 1 forced astronomers to expand the definition of what an LSB galaxy could be. It cracked open a new subcategory, the giant LSB spiral. And though a few more examples have emerged since, none come close to matching Malin 1 in scale or elusiveness. But why is its surface brightness so low? A major factor is star formation efficiency. In Malin 1's disk, the density of gas and dust, though vast in total, is spread thin over hundreds of thousands of light years. This makes it difficult for the interstellar medium to collapse into new stars. Without dense regions and high-pressure zones to spark stellar birth, the galaxy lacks the luminous, young star populations that typically light up spiral arms. What stars do exist are older, cooler, and emit less light. Another factor is the galaxy's stellar population distribution. In typical galaxies, stars are more concentrated toward the center and along spiral arms, producing visible patterns. But in Malin 1, the stars are distributed much more diffusely. Their combined light just isn't enough to make the galaxy bright when viewed from afar. Add to this the vast scale. Remember, Malin 1 is 6 times larger than the Milky Way, and you get a structure so thinly populated with luminous matter that it essentially disappears unless you know precisely where and how to look. And here's where Malin 1 earns its crown. Not only is it the largest known spiral galaxy, but it is also the most extreme example of low surface brightness in a structured giant. Other LSB galaxies may be fainter, but they lack the size. Other giant galaxies may be larger, but they shine brightly. Malin 1 stands alone at the crossroads, a majestic spiral skeleton cast in starlight so faint it becomes part of the dark. This has profound implications for our understanding of the universe. If such massive galaxies can exist almost undetected, it raises the possibility that we are missing many more. Malin 1 is not just rare, it is representative of a hidden frontier in galaxy research. It tells us that our view of the cosmos may be biased, not by our understanding, but by our instruments. We are attuned to light. We build telescopes to chase it. But Malin 1 shows us that the largest structures in the universe may be quiet, dark, and nearly invisible. In a way, Malin 1 challenges the very premise of astronomical discovery. It teaches us that true cosmic giants don't need to shine. They don't need to burn brightly to command attention. Sometimes, they just exist, silently, massively, waiting for someone to develop the patience, technique, and curiosity to notice them. Malin 1 is not just a low-surface brightness galaxy. It is the sovereign of shadows, the quiet king of the cosmic wilderness, and the undisputed ruler of the faintest spiral frontier we've ever seen. Stand beneath the night sky with a telescope, and you open a portal into the cosmos. Planets, nebulae, galaxies all waiting to reveal themselves through lenses and mirrors. But for all their power, even the most advanced optical telescopes are still slaves to light. They require photons, streams of electromagnetic energy within the visible spectrum, to reveal what's out there. And this is where Malin 1 executes one of the most profound vanishing acts in astronomy. Despite its monstrous size, despite its intricate spiral structure and massive disk of gas and stars, you cannot see it through a normal telescope. Not because it's too far, though it is distant. Not because it doesn't exist, but because it refuses to shine. To understand why Malin 1 is invisible to traditional telescopic observation, we have to examine the fundamentals of how telescopes work. Optical telescopes, those that capture visible light, rely on gathering enough photons from an object to create an image. The brightness of a celestial object in the night sky isn't just about how much total light it emits. It's also about how concentrated that light is across a given area of sky. This is why the concept of surface brightness is crucial. A small but concentrated object, like a quasar, can shine brilliantly, while a vast but diffuse structure like Malin 1 can remain hidden in plain sight. When astronomers point a telescope at the sky, they are not only fighting distance, they are battling contrast. The Earth's atmosphere itself glows faintly, creating what's called sky glow, a subtle, constant background brightness caused by airglow, zodiacal light, and scattered urban illumination. To see faint galaxies, an object must emit more light per unit area than this background level. But Malin 1's surface brightness in many regions is lower than the natural sky background, even in the darkest, clearest, most remote observatory locations on Earth. This means that, when looking for Malin 1 through an optical telescope, its extended disk simply gets lost in the noise. The telescope might detect the bright core, a small, elliptical-looking blob near the center, but the enormous arms that stretch hundreds of thousands of light-years outward will not register as distinct features. They are not invisible in the literal sense, but rather their light is so thinly spread that it's swamped by the background, like a single candle in a fog-covered stadium. This phenomenon becomes even more problematic when you consider exposure time. Most amateur telescopes and even many professional sky surveys operate on relatively short exposures, minutes or hours at most. While that's sufficient for bright galaxies and stars, it's completely inadequate for ultra-faint objects like Malin 1. Detecting its full extent requires extremely long exposures, sometimes totaling dozens of hours, and advanced image processing techniques to tease out the subtle gradients of light hidden deep in the background noise. Even powerful instruments like the Hubble Space Telescope, famed for its stunning images of faraway galaxies, struggle with Malin 1. Though Hubble can resolve the bright central region with excellent clarity, it cannot easily capture the extended arms of the galaxy. That's because Hubble's field of view is relatively narrow, and its imaging sensors, while extremely sensitive, are still optimized for objects with higher surface brightness. In fact, Hubble images of Malin 1 show it as an unassuming spiral, giving no clue to its true size unless paired with radio or multiband data from other observatories. Part of the problem also lies in wavelength limitations. Malin 1, like all LSB galaxies, emits very little light in the visible band. The majority of its outer structure emits weakly in the radio and infrared regions of the spectrum, wavelengths that traditional optical telescopes are not equipped to detect. Instruments must be specifically tuned to longer wavelengths to catch the signals from the vast hydrogen clouds that mark Malin 1's disk. That's why radio telescopes and deep sky surveys, such as those from the Sloan Digital Sky Survey (SDSS), have been more successful in uncovering its full extent. Additionally, telescopes and surveys often apply automated detection algorithms that filter out noise and search for patterns consistent with typical galaxies. These algorithms often overlook or discard faint, diffuse structures as background fluctuations or processing artifacts. Malin 1, being exactly the kind of galaxy these filters tend to ignore, has likely slipped past unnoticed by many sky surveys over the decades. This issue points to a built-in observational bias in astronomy. We find the galaxies that shine, and we miss the ones that don't. Compounding the difficulty is the distance to Malin 1, about 1.2 billion light-years away. That means even the brighter parts of the galaxy are dimmer simply due to cosmological redshift and the inverse square law of light. Its light has traveled across time and space, redshifted and stretched, arriving at Earth more faint and diffuse than it originally began. To spot such a distant and diffuse object with any clarity requires exceptional sensitivity and focus. But perhaps the most poetic element of Malin 1's invisibility is this: it is hiding not in darkness, but in light. Its faint spiral arms are there, stretched across hundreds of thousands of light years, but drowned out by the cumulative light of stars, galaxies, dust, and background glow that fills every patch of sky. The galaxy is quite literally outshined, not by something nearby, but by the universe itself. This is why the discovery of Malin 1 in 1986 was so remarkable. It wasn't found through normal observation. It was discovered by David Malin, an astronomer using enhanced photographic plate techniques to dig deeper into the images than anyone else had. He amplified contrast, increased dynamic range, and carefully processed the photographic plates taken at the Anglo-Australian Observatory. Only then did the enormous structure of Malin 1 emerge like a phantom from the fog. And so, despite being one of the largest spiral galaxies ever observed, Malin 1 remains invisible to most telescopes, not because of its absence, but because of our limitations. It is a cosmic monument that challenges the very tools we use to explore the universe. It whispers a cautionary tale, that the cosmos may be full of wonders we simply haven't looked hard enough to see. In a universe that often dazzles us with brilliance, Malin 1 is a reminder that some of its greatest marvels lie not in the stars that shine, but in the light that's too faint to find, unless you're willing to look beyond the obvious, beyond the visible, and into the hidden structure of the dark. Malin may first be one of the largest spiral galaxies ever discovered, but when you try to tally up all the visible matter inside it, every star, every speck of dust, every glowing thread of hydrogen gas, you're left with a sobering conclusion: it doesn't add up. The stars are too few. The light is too dim. The mass we can see, even when stretched across 650,000 light-years, simply cannot account for the galaxy's structure, stability, or rotation. And that leads us into one of the most profound truths of Malin 1's existence. It is made mostly of nothing you can see. Enter dark matter. The moment astronomers began charting the motions of Malin 1, its rotation, its gravitational cohesion, the way its outer arms continue to orbit smoothly rather than flying apart, they knew something invisible had to be at play. If Malin 1 were made up solely of the luminous matter we can detect, stars and gas and dust, then its extended spiral arms should have long ago become unstable. The gravitational pull from the core would not be strong enough to keep the outer disk in orbit. Yet those arms move in coherent rotation, sweeping silently through the void, obeying a gravitational blueprint drawn by something unseen. This invisible substance, this unseen scaffolding, is dark matter, the mysterious form of matter that does not emit, absorb, or reflect light. It doesn't shine in any wavelength, it doesn't form stars, and it doesn't clump together in the familiar ways normal matter does. But it exerts gravitational influence. In fact, dark matter makes up an estimated 85% of the total matter in the universe, and galaxies like Malin 1 provide some of the clearest evidence for its existence. In a galaxy with such an enormous disk and so little light, the gravitational math becomes even more startling. For Malin 1 to remain structurally intact, to rotate as a unified system and maintain the coherence of its arms over cosmic time scales, it must be enveloped in a vast halo of mass that we cannot see. This halo doesn't merely supplement the galaxy structure, it dominates it. Estimates suggest that as much as 95% or more of Malin 1's total mass is in the form of dark matter. That means only about 1 in every 20 particles making up this galaxy is visible. The rest is dark, cold, and fundamentally mysterious. This dark matter halo likely extends far beyond the luminous disk, possibly millions of light-years across. It is what binds the galaxy together, giving it its gravitational profile, dictating how its arms rotate, and ensuring that its slow, massive sweep through space does not unravel. Without dark matter, Malin 1 would disintegrate under its own rotational dynamics. The stars in the outer disk would fly away into the void, and the spiral pattern would collapse into chaos. In fact, when astronomers measured the rotation curve of Malin 1, a plot of how fast different parts of the galaxy rotate around the center, they saw something that didn't match Newtonian expectations. In a galaxy governed solely by visible mass, the rotational velocity should drop off at greater distances from the center. But Malin 1's rotation curve remains flat even far out in the faint, distant spiral arms. This is the classic fingerprint of dark matter. The outer parts of the galaxy are moving faster than they should be if only visible matter were involved. This extra velocity demands extra gravity, and the only candidate providing that pull is dark matter. Malin 1, with its faint disk and weak surface brightness, becomes one of the best laboratories for studying dark matter's role in galactic formation. In bright galaxies, the light of stars can confuse the signal. But in Malin 1, where stars are few and far between, the gravitational behavior can be attributed almost entirely to the hidden mass. It is a galaxy that wears its dark matter heart on its sleeve, an enormous, invisible force field shaping a delicate spiral structure of starlight and gas. What's more, the distribution of this dark matter appears to be unusually smooth. In many galaxies, the dark matter halo is clumpy or distorted due to past mergers or gravitational interactions. But Malin 1's halo seems remarkably coherent, possibly indicating a long, undisturbed evolutionary history. That, in turn, may explain why the galaxy could grow so large and remain so faint. Without the chaotic violence of collisions to compress gas and trigger starbursts, it retained a dark and quiet nature. This dominance of dark matter also changes how we think about galaxy classification. If galaxies like Malin 1 exist, giant spirals built on nearly invisible scaffolding, how many others have we missed? Could there be entire populations of massive galaxies whose light is simply too thin to detect, but whose gravitational fingerprints shape the dynamics of galaxy clusters, filamentary structures, and cosmic voids? In this way, Malin 1 becomes more than just a peculiar object, it becomes a key to the hidden cosmos. Its very existence proves that gravity can sculpt vast, elegant structures even when the luminous content is sparse. It shows that dark matter isn't just a side character in the cosmic drama, it's the architect. And yet, despite its dominance, we still don't know what dark matter is. We don't know if it's made of undiscovered particles, if it interacts via unknown forces, or if it's a sign that our understanding of gravity needs to evolve. But what we do know is this: Malin 1 would not exist without it. When you look at the dim glow of Malin 1's arms, when you trace the faint outline of a spiral reaching across 500,000 light-years, you are seeing the result of dark matter in action. You are witnessing the shape of the invisible, the structure of the unknown. Malin 1 is made mostly of nothing you can see. But in that nothingness lies the silent force that binds galaxies, sculpts the universe, and holds the cosmos together. The moment astronomers began mapping the motion of stars and gas in galaxies, something strange emerged, a mystery that continues to echo through every corner of modern astrophysics. That mystery lives not in how fast galaxies spin, but how their rotation behaves across their vast disks. And in the case of Malin 1, the mystery becomes even deeper. For here is a galaxy whose rotation curve does more than just confuse, it defies the expectations set by its visible mass, acting as a gravitational ghost story written across more than 500,000 light-years. In a typical spiral galaxy governed by the rules of Newtonian physics and containing only visible matter, the rotation of stars and gas should follow a predictable pattern. Near the galactic center, where mass is most concentrated, orbital velocities rise rapidly. But as one moves farther out, into regions where there's less visible material, those velocities should drop off, similar to how the outer planets in our solar system move more slowly than the inner ones. This is what Kepler's laws of motion would predict. Less mass means less gravity, and less gravity means slower orbital speeds. But that's not what we see. In galaxy after galaxy, rotation curves, graphs plotting orbital velocity versus distance from the center, do not fall. Instead, they flatten out. Even far from the core, where stars are few and starlight fades, the orbital velocities remain high. This is not just a quirk, it's a consistent, measured phenomenon. And it's especially striking in Malin 1, where the outer disk extends hundreds of thousands of light-years into regions so faint, so devoid of visible stars, that the rotation should crawl to a halt. But it doesn't. The stars and gas in Malin 1's farthest spiral arms continue orbiting at roughly the same velocity as material much closer to the core. The implication? There is far more mass in Malin 1 than we can see, and it's not just a little bit more. The visible matter, stars, dust, and glowing hydrogen, makes up only a fraction of what must be present to keep the galaxy rotating as it does. In fact, based on the galaxy's rotation profile, more than 90% of Malin 1's mass is invisible. And this is not speculation, it's mathematics. Astronomers measure rotation curves by tracking the Doppler shifts in the light emitted from different parts of a galaxy. If a portion of the galaxy is rotating toward us, its light shifts slightly toward the blue end of the spectrum. If it's rotating away, the light shifts toward the red. By mapping these shifts across the disk of a galaxy, scientists can construct a velocity profile, one that reveals how fast different parts are spinning. Malin 1's Doppler data is astonishing. Even at extreme distances from the galactic core, far beyond where most galaxies would have any measurable rotation, Malin 1's outer disk keeps moving at speeds that require a gravitational well far deeper than visible matter can provide. This flat rotation curve is a smoking gun. It demands either an enormous halo of unseen mass, what we call dark matter, or a radical overhaul of our understanding of gravity itself. But the mystery is compounded by Malin 1's low surface brightness. In high surface brightness galaxies like the Milky Way, the inner regions are so densely packed with stars that even without dark matter, you'd still get substantial orbital velocities near the core. But Malin 1's entire disk is diffuse. Even its center isn't exceptionally bright. If visible matter were the only factor, the whole rotation curve should be lower across the board. The fact that it isn't, the fact that it stays flat at such great distances, means that Malin 1's dark matter halo must not only exist but must be extraordinarily massive and smoothly distributed. In many ways, Malin 1 presents an extreme test case for the dark matter hypothesis. In brighter galaxies, it can be tricky to separate the gravitational influence of visible matter from that of dark matter, especially in dense, complex cores. But in Malin 1, where luminous matter is so spread out, the gravitational contribution of dark matter becomes dominant and clear. It's as though we're watching a ballet performed on a stage lit only by shadows, no spotlight, just the graceful motion of invisible forces guiding stars along their paths. Interestingly, the flatness of Malin 1's rotation curve might also hint at the age and stability of its dark matter halo. In many galaxies, halos are thought to form early in the universe's history and evolve over time through interactions, mergers, and accretion. Malin 1's halo appears to be smooth and symmetric, suggesting it may have had a quiet evolutionary history, undisturbed by major collisions that could disrupt the halo's coherence. That, in turn, could explain the extraordinary extent of its disk. It had the time and gravitational stability to grow slowly and widely, without the chaos that triggers starburst formation and disk thickening in other galaxies. The implications stretch far beyond Malin 1. If such a vast, low-density, dark matter-dominated system can maintain structural stability across more than 500,000 light-years, then it forces a re-evaluation of how galaxies form and evolve. It suggests that under the right conditions, namely, an abundance of dark matter and a calm cosmic environment, a galaxy can form that looks almost nothing like what we're used to. Faint, sprawling, and graceful, but underpinned by a gravitational behemoth we cannot see. Some have proposed alternative explanations. Modified gravity theories like modified Newtonian dynamics, attempt to explain flat rotation curves without invoking dark matter at all. These theories adjust how gravity behaves at very low accelerations. But while MOND can sometimes reproduce galaxy rotation curves in high-brightness systems, it struggles with giants like Malin 1, where the discrepancy between visible mass and required gravity is too great. For now, the dark matter explanation remains the most compelling, and Malin may first be one of its strongest supporting cases. In a sense, the rotation of Malin 1 is like a fingerprint left by the universe's invisible hand. The arms of the galaxy sweep silently through space, not because of the light we see, but because of the mass we don't. It is one of the clearest demonstrations that gravity listens not to what shines, but to what is truly there. And in Malin 1, what is truly there is something vast, hidden, and waiting to be understood. The mystery of its rotation curve is not just a technical detail, it is the heartbeat of the galaxy, pulsing in dark matter rhythms, echoing a truth that defines modern cosmology, that what we cannot see may shape more of reality than what we can. In a universe where light is often our only clue, Malin 1 demands we look deeper. It's not just faint, it's quietly radical. The laws of motion etched into its colossal spiral arms, the gravitational grip that keeps those arms from drifting apart, and the persistence of rotational velocity across incomprehensible distances all whisper a truth that astronomers have come to accept with equal parts awe and unease. Malin 1 makes no sense unless most of its mass is invisible. The evidence for dark matter in this galaxy isn't anecdotal or circumstantial. It is mathematical. It is gravitational. It is etched into the very structure and dynamics of the galaxy itself. And while the concept of dark matter was already well established before Malin 1's discovery, this galaxy would become one of its most elegant testaments. The starting point for this evidence is found in the gravitational behavior of matter within the galaxy. If you count all the visible mass, stars, gas, dust, you can estimate how much gravitational force it should exert. Then you compare that to the observed motions of the stars and gas orbiting at various distances from the center. In Malin 1, this comparison leads to a stunning mismatch. The luminous matter accounts for only a tiny fraction of the gravitational force necessary to explain the galaxy's rotation. The stars at the outer edge are moving far too quickly for the gravity of visible matter alone to keep them in orbit. In Newtonian physics, they should have flown off into intergalactic space long ago. But they haven't. They're still orbiting. Quietly. Steadily. Over hundreds of thousands of light years. That can only mean one thing: there's additional mass we can't see. This is not unique to Malin 1, it's a phenomenon observed in countless spiral galaxies. But Malin 1 magnifies the problem by several orders of magnitude. Its visible matter is so spread out, so faint, that the discrepancy between expected and observed rotation is much more extreme than in normal galaxies. This creates a nearly perfect stage to isolate the effects of dark matter. In galaxies with high surface brightness, the gravitational pull of luminous matter can cloud the data. But Malin 1's luminous matter is too sparse to confuse the issue. Whatever is holding the galaxy together, it's not stars. It's not glowing gas. It's something else entirely. The most direct evidence for this comes from analyzing the rotation curve of the galaxy. As discussed previously, Malin 1's rotation does not decrease with distance from the center, it remains flat. This is a signature of dark matter. It indicates that the galaxy is embedded in a massive, roughly spherical halo of invisible matter, extending well beyond the luminous disk. The only way to maintain such high rotational velocities in the outer regions, where there are almost no visible stars or gas, is to have an enormous mass component distributed throughout the halo. Further confirmation comes from studying the mass-to-light ratio. This ratio compares the total mass of a galaxy, as inferred from its dynamics, to the amount of light it emits. For galaxies like the Milky Way, the mass-to-light ratio is relatively modest, maybe 10 to 20. But in Malin 1, the mass-to-light ratio is staggeringly high, estimated to be well over 100 in some regions, and potentially even higher when including the extended halo. That means for every unit of light the galaxy emits, there are more than 100 units of mass lurking unseen. And what's even more remarkable is that Malin 1 appears to have a normal composition of visible matter, just not very much of it per unit volume. Its central bulge contains older, redder stars. Its disk has plenty of hydrogen gas. There's nothing exotic about the visible stuff, it's just not enough. The galaxy's dynamics only make sense if most of the mass is something else entirely. Something that doesn't emit light. Something that doesn't form stars. Something that is, for all practical purposes, invisible. Astronomers have also mapped the distribution of neutral hydrogen, HI, in Malin 1 using radio observations. This neutral hydrogen extends far beyond the visible disk and follows the flat rotation profile, serving as a tracer for the galaxy's gravitational field. But again, the mass of this hydrogen is far too low to account for the rotation on its own. It's another pointer toward the unseen, tracing the edge of a gravity well that stretches well past the visible stars. Alternative explanations, such as the galaxy being in a special phase of development, or its stars somehow moving under unusual conditions, don't hold up under scrutiny. The physics is straightforward. If there is not enough visible mass to account for the motion, and if the motion is real, which it is, thanks to direct Doppler measurements, then the only viable conclusion is that most of the mass is not visible. That is dark matter by definition. What's striking is just how clean the case is in Malin 1. In many galaxies, debates over dark matter involve messy cores, complex mergers, or interfering feedback mechanisms. Malin 1, by contrast, is relatively isolated and evolutionarily quiet. This makes it a near-ideal laboratory for testing dark matter models. There are fewer competing gravitational influences. Fewer nearby galaxies to complicate things. Just a vast spiral drifting through space, whose only real secret is how it holds itself together. The implications are enormous. Malin 1's structure suggests that dark matter isn't just an add-on. It's a fundamental framework on which galaxies can form. It means that galaxies like Malin 1 didn't just form in spite of their low star density. They may have only formed because the dark matter was there to anchor them. In other words, Malin 1 is not just dominated by dark matter, it is shaped, structured, and stabilized by it. This supports the broader cosmological picture we have today, that the visible universe, the stars, planets, gas clouds, and galaxies, is just the tip of the iceberg. Beneath it lies a hidden universe made of dark matter, structuring the cosmic web, influencing galaxy formation, and guiding the large-scale behavior of the cosmos. Malin 1 makes that invisible world impossible to ignore. It is a galaxy so faint it's nearly transparent, but so massive it cannot be dismissed. And it tells us, with every rotation of its immense arms, that the true mass of the universe lies not in the light we see, but in the darkness we cannot. If you could stand at the edge of Malin 1, some 325,000 light-years from its center, and look back across its titanic spiral arms, you wouldn't see a brilliant field of stars like in the Milky Way. Instead, you'd see a vast ocean of darkness, barely punctuated by the faintest glimmer of ancient suns. Malin 1 is not a galaxy ablaze with youthful energy. It is quiet, subdued, almost slumbering. And that's because Malin 1, for all its mass and size, is gas-rich but star-poor. This paradox is one of the most fascinating and confounding aspects of the galaxy. In most spirals, where you find large reserves of gas, you expect to find vibrant regions of star formation, shimmering clouds of newborn stars and supernovae, glowing emission nebulae sculpted by ultraviolet radiation, and dense clusters forming inside molecular clouds. But Malin 1 bucks this trend. It has the raw ingredients, plenty of neutral hydrogen gas, Hi, yet it produces stars at an astonishingly low rate. Its disk is like a colossal engine running at idle, full of fuel, but barely burning. Radio observations, especially from powerful facilities like the Very Large Array, VLA, have revealed that Malin 1's hydrogen reserves are enormous. In fact, the total mass of neutral hydrogen gas in Malin 1 is among the highest ever recorded for a spiral galaxy. This gas extends far beyond the visible disk, and it moves in graceful, ordered rotation, hugging the same flat rotation curve shaped by the galaxy's dark matter halo. So, with so much gas present, why are there so few stars? The answer lies in the density of that gas. Star formation doesn't just require gas. It requires gas that is dense enough to collapse under its own gravity. In most galaxies, that collapse is triggered when clouds of gas collide, compress, or become gravitationally unstable. These denser regions, often less than a few hundred light-years across, become cradles for star birth. But in Malin 1, the gas is incredibly diffuse, spread out across such a vast area that it never reaches the critical density needed for collapse. Think of it this way. Take a swimming pool's worth of water and pour it into a glass. It's obvious and concentrated. Now take that same swimming pool of water and spread it across an entire football field. It's still there, but it's so thin you might not even know it. That's what's happening in Malin 1. The gas is present, but it's so thinly distributed that the gravitational pressure needed to form stars just isn't there. The Q parameter, a mathematical condition for disk stability against gravitational collapse, is likely too high across most of Malin 1's disk, meaning the gas is too stable to fragment into stars. Another factor is the lack of triggering mechanisms. In normal spiral galaxies, spiral density waves, like ripples in a pond, compress gas along spiral arms, forming stars in rhythmic bursts. Collisions with nearby galaxies or the passage through intergalactic filaments can also stir up gas and spark star formation. But Malin 1 is isolated. It appears to have evolved in a quiet pocket of space, untouched by major interactions. This piece might be part of why its gas has remained in place, thin and undisturbed, for billions of years. Moreover, the stars that do exist in Malin 1 are mostly old and red, indicating that star formation likely peaked eons ago and has since dwindled to a trickle. There is very little evidence of massive, hot, young stars, those that light up star-forming regions with blue-white brilliance and ionize surrounding gas into the colorful structures we see in starburst galaxies. Without those energetic young stars, there are no glowing clouds to reveal star-forming regions, and very few supernovae to stir and compress the interstellar medium. This has a compounding effect. Star formation isn't just a process, it's a feedback loop. Massive stars go supernova and inject energy into the surrounding gas, compressing it, stirring it, and often triggering the next generation of stars. But in Malin 1, with few massive stars and rare supernovae, the feedback loop is broken. The galaxy remains passive. The gas remains calm. And so star formation stays low. This leads us to the concept of star formation efficiency, SFE, a metric that compares how much star mass forms from a given amount of gas. In Malin 1, the SFE is extraordinarily low. Some models estimate that only a tiny fraction of a percent of the galaxy's available gas is being converted into stars over time. That puts Malin 1 in a class with so-called dark galaxies, those with high gas content but almost no starlight to show for it. While Malin 1 doesn't quite cross into that territory, since it does have a defined stellar population, it straddles the edge between luminous and dark. The implications for galactic evolution are enormous. Malin 1 represents a different path, a galaxy that didn't race into brilliance or collapse into bursts of star formation. Instead, it grew slowly, gently, forming stars at a trickle and preserving its gas over eons. It may continue doing this for many billions of years, never igniting, never collapsing, simply coasting through the cosmos, a quiet reservoir of potential. And this opens up tantalizing questions. Could Malin 1 eventually burst into life if something disturbed its balance? A passing galaxy or a shift in its dark matter distribution could compress the gas and light up the disk in a sudden burst of new stars. Or perhaps it will remain this way forever, silent, massive, and dim, never fulfilling the promise of its enormous gas reserves. Malin 1 is like a cosmic vault, packed with raw materials, but sealed shut. Its hydrogen clouds drift lazily in its gravitational arms, waiting for a spark that may never come. And yet, in this tranquility, it tells us something vital about galaxy formation, that light and life are not inevitable. That size does not guarantee brilliance. That the universe has many ways to build its structures, and not all of them are lit by stars. In Malin 1, we see not a failure, but a reminder. The cosmos is vast enough for silence. Not every galaxy is a furnace. Some are slow, cold, and content to drift, shaped by darkness, carrying the possibility of light without ever needing to ignite. Malin 1 is the very opposite of a cosmic fireworks show. Where other galaxies roar with radiation, buzz with supernovae, and dazzle the universe with blue-white brilliance from hot young stars, Malin 1 simply glides. It does not rush, it does not burn brightly, and it does not erupt with bursts of new life. It is what astronomers call a slow, quiet galaxy, and in a cosmos filled with chaotic mergers, high-energy collisions, and seething galactic cores, this silence is profound. To grasp just how calm Malin 1 is, consider what we usually associate with active galaxies. Starburst galaxies, like Messier 82 or the Antennae galaxies, form stars at furious rates, sometimes producing thousands of solar masses worth of stars each year. These galaxies are dynamic, turbulent, alive with energy. Their interstellar medium is thick with shock waves and ionized clouds, driven by intense stellar feedback. They glow in ultraviolet, spew out X-rays from supernova remnants, and churn out powerful galactic winds. In contrast, Malin 1 forms stars at a pace so slow it's almost geological in its rhythm, perhaps a few solar masses per year, or even less, across a disk that spans more than 650,000 light-years. The tranquility of Malin 1 is written into its entire structure. Its gas is stable and diffuse. Its stars are ancient and faint, quietly circling the core without drama. Even its central bulge, typically the most crowded and energetic region of a spiral galaxy, is subdued. There's no evidence of a raging active galactic nucleus. No supermassive black hole feeding in a frenzy. No jets of relativistic particles slicing through space. Instead, the core is serene, home to older, redder stars that long ago finished their fireworks and settled into quiet senescence. This calmness extends to Malin 1's dynamical state. The galaxy exhibits ordered rotation, with little sign of recent gravitational disturbances. There are no large tidal tails, no signs of disrupted arms, no violent distortions that would indicate past collisions or interactions. In the high-density regions of the universe, galaxy clusters, cosmic filaments, or even galaxy groups, gravitational interactions are common. These encounters trigger starbursts, deform disks, and rearrange galactic structure. But Malin 1 appears to have avoided all that. It sits in a relatively isolated region of space, untouched by chaos, evolving at its own leisurely pace. Such a slow evolution means Malin 1 has retained its original structure for billions of years. While many spiral galaxies are thickened and scrambled by interactions, Malin 1 remains astonishingly thin and diffuse, almost fragile. Its spiral arms are like gossamer threads stretched across the void, maintained not by collision-driven compression but by the quiet tug of a dark matter halo and the low-density gas within. The galaxy's metallicity, a measure of how enriched it is with heavier elements, also tells a story of slowness. Stars create heavier elements through nuclear fusion, and supernovae spread those elements into the interstellar medium. In galaxies where stars form rapidly, metals build up quickly. But in Malin 1, with its low star formation rate, the buildup of metals is slow and sparse. This means that even now, after billions of years, much of the galaxy remains relatively chemically pristine. The gas here is similar in composition to the early universe, rich in hydrogen and helium, poor in elements like carbon, oxygen, and iron. This chemical simplicity reinforces the idea that Malin 1 is cosmically conservative. It has barely dipped into the resources it was born with. It still holds vast quantities of raw material, but has spent only a tiny fraction of it making stars. In a universe where many galaxies rush through their fuel and burn brightly before fading out, Malin 1 is a model of restraint. It is, in every sense, a galaxy of endurance rather than spectacle. Its tranquil nature also makes it incredibly valuable to astronomers. While violent galaxies can be more visually striking, their internal processes are often masked by chaos. Malin 1, by contrast, offers a clear view of galactic dynamics in a low-activity regime. It shows how a galaxy can exist not in the grip of collisions or starbursts, but in long-term gravitational harmony. It's like studying a calm lake rather than a stormy ocean. You can see the underlying structure more clearly. Moreover, this serenity challenges our assumptions about what galaxies are supposed to be. Malin 1 forces us to ask, is vigorous star formation necessary for a galaxy to be considered alive? Can a galaxy with minimal starlight still be seen as evolving? And what role do such quiet giants play in the cosmic balance? If they are numerous but faint, they could represent a hidden population of massive systems shaping the universe behind the scenes. The idea of quiet, in a galactic sense, does not mean lifeless. It means unhurried, undisturbed, and continuous. Malin may first not shine with the urgency of youth, but it persists, moving slowly through the cosmos, changing over timescales longer than human imagination. Its beauty lies not in brilliance, but in patience, in endurance, in the slow sculpting of stars from diffuse gas under the steady pull of gravity. Malin 1 is a whisper in a universe full of shouts. And yet that whisper may be far more common, and far more important, than we ever imagined. It is proof that not all galaxies are born to blaze. Some are built to last. Malin 1 drifts through one of the quietest corners of the observable universe, lying deep within the boundaries of the faint northern constellation known as Coma Berenices. Berenice's hair. This name itself is poetic, taken from the legend of Queen Berenice II of Egypt, who sacrificed her flowing locks to the gods, and in return, her hair was placed among the stars. But hidden within this region of myth and faint glimmers lies something far more grand and mysterious, a colossal, nearly invisible galaxy, gliding through the void like a forgotten ghost of cosmic history. Located at an estimated distance of 1.2 billion light-years from Earth, Malin 1 is unimaginably far from our solar system. That means when we observe it today, we're not seeing it as it is now, we're seeing it as it was 1.2 billion years ago, during a time when Earth's continents looked completely different, when multicellular life was just beginning to take recognizable form, and long before dinosaurs ever walked the planet. Its light, what little of it reaches us, has taken more than 1 billion years to make the journey across the expanding fabric of space, climbing out of the gravitational wells of galactic halos, passing through vast intergalactic voids, and stretching its wavelength all the way into the red part of the spectrum. This extraordinary distance also helps explain why Malin 1 remained undiscovered for so long. Its faintness alone would challenge even the most powerful telescopes. But combined with its remote location, the galaxy effectively cloaked itself from our instruments for decades. It's not simply hidden in the dark, it's removed by time itself, placed in a region of the cosmos where few telescopes dared to look for such delicate structures. The Coma Berenices region of the sky is not empty, far from it. It's home to the Coma Cluster, a rich collection of over 1,000 galaxies, many of which are elliptical in shape and densely packed into a cosmic metropolis about 300 million light-years away from us. But Malin 1 is far beyond that cluster, much deeper into space and nowhere near the gravitational bustle of the Coma Cluster's tightly bound galaxies. In fact, one of the defining features of Malin 1's location is its remarkable isolation. Unlike most massive galaxies, which live in busy neighborhoods and interact frequently with nearby companions, Malin 1 appears to exist in a quiet suburb of the universe, far from the gravitational jostling that typically shapes galactic evolution. This solitude has major implications for its structure and history. In denser regions of space, galaxies collide, merge, and distort one another over time. These violent events compress gas clouds, triggering waves of star formation, thickening galactic disks, and scrambling spiral patterns. But Malin 1 seems to have been spared that chaos. Its incredible size, thin disk, and low star formation rate all point to a gently evolving system, one that grew slowly without the interruption of major galactic interactions. The cosmic environment around Malin may first also be unusually devoid of smaller satellite galaxies, the kind that often serve as the building blocks for larger spirals through a process known as hierarchical merging. This lack of mergers may have allowed Malin 1 to maintain its delicate spiral structure and vast disk without growing a dense, bulging core or triggering bursts of star formation. Its surroundings seem to have been just empty enough, just quiet enough, to let it become what it is, a massive, dark matter-dominated, low-surface brightness galaxy with an identity all its own. Interestingly, despite its remoteness, Malin 1 still obeys the same cosmic rules that govern galaxies everywhere. It rotates, it binds matter together, it hosts stars and gas. But it does all of this in a near-perfect vacuum of attention. It doesn't light up the night sky. It doesn't dominate the regions around it. It simply exists, enormous and ancient, moving through one of the loneliest regions of the observable universe. This location also plays a role in how we perceive the galaxy from Earth. The farther away an object is, the smaller its angular size appears, even if its true physical size is enormous. Because of this, Malin 1 appears as just a faint smudge in even long-exposure images. To the untrained eye, it doesn't look like a spiral at all. It looks like a ghost on a fogged lens, its structure almost indistinguishable from the cosmic background. Only by carefully analyzing the light and motion within that smudge have astronomers been able to piece together the vast, complex galaxy beneath. Malin 1's position also raises broader questions about the distribution of similar galaxies throughout the cosmos. If such a giant could hide in a relatively well-observed region like Coma Berenice's, how many other ghost galaxies are waiting in even quieter, less studied parts of the sky? Are there thousands more Malin-class galaxies drifting through the voids between clusters, too faint, too spread out, too distant to catch the attention of conventional sky surveys? The answer could reshape our understanding of cosmic structure. For now, though, Malin 1 remains a unique sentinel in the far reaches of space, a solitary titan in the direction of Berenice's celestial hair. It's a reminder that even in the faintest corners of the universe, even in the places we almost never look, there can be wonders beyond scale, quiet, distant, and utterly breathtaking. Malin 1's extraordinary size and ghostly stillness are not just features, they're consequences. One of the most compelling aspects of this galactic behemoth is not only what it is, but where it is, and more importantly, where it's not. It's not near any significant galaxy clusters. It's not tangled in the gravitational drama that shapes many other large galaxies. It's not being pulled, twisted, or merged into something else. Malin 1 is alone, and that isolation might be the single most important reason it exists in such an unusual form. In the cosmic landscape, most galaxies are social. They form in groups or clusters, environments filled with complex gravitational interactions. In these environments, galaxies tug on one another, collide, merge, and cannibalize. These processes drive galaxy evolution, transforming spirals into ellipticals, triggering intense starbursts, or tearing apart delicate structures with tidal forces. Interactions are common, and they often leave lasting scars, warped disks, irregular halos, hot gas stripped from galactic cores, or massive central bulges grown from mergers. But Malin 1 shows none of that chaos. Its enormous, ultra-thin disk and faint spiral structure are intact, suggesting a galaxy that has never undergone a major merger. Or if it did, it was an exceptionally long time ago, and the disturbance has long since settled into symmetry. This kind of preservation is almost impossible in crowded regions of the universe. In the dense cores of clusters like Virgo or Coma, galaxies routinely pass close to each other, stirring up their internal structures, exchanging gas, and collapsing under the violence of interaction. Spiral arms become ragged. Star formation explodes in brief, unsustainable bursts. Black holes are awakened in central regions, sending jets of particles across thousands of light years. But Malin 1 appears to have sidestepped all of this. Its structure suggests a galaxy that has had time and space to grow slowly, without interruption. Its location, far beyond the crowded lanes of the Coma cluster, puts it in a low-density environment, likely a cosmic void or the thin strands of a filament on the cosmic web. These are the regions of the universe where matter is sparse, where the gravitational dance is slower and quieter. Galaxies here can drift for billions of years without ever encountering a close neighbor. And in that tranquility, they can evolve along very different lines than their cluster-bound counterparts. This isolation helps explain why Malin 1 is so diffuse. In more active environments, galactic gas gets compressed by ram pressure, tidal forces, or intergalactic winds. That compression leads to higher star formation rates, denser disks, and brighter bulges. But Malin 1, lacking these external pressures, was never forced to collapse quickly. Its gas remained relaxed, its density stayed low, and its star formation proceeded at a crawl. The result is a galaxy that formed not in flashes, but in layers thin, wide, and stretched across space like an ancient fog bank, shaped only by its own inertia and gravity. There's also the question of dark matter dynamics. Malin 1's massive dark matter halo likely contributed to stabilizing it against disturbances. But without isolation, even a strong halo can't save a galaxy from being swallowed or stirred by larger neighbors. The calmness of its environment may have helped preserve not just its structure, but the integrity of its halo itself, allowing it to remain symmetrical and undisturbed, which in turn maintained the flat, orderly rotation we observe today. What's more, the lack of neighboring galaxies means there was little opportunity for satellite accretion, the process by which large galaxies absorb smaller ones over time. This is one of the main ways galaxies grow their bulges and halos, and it's one of the primary engines of starburst activity. But Malin 1 seems to have missed out on this process, or avoided it altogether. Its smooth disk and relatively undeveloped central bulge suggest that it hasn't fed on other galaxies in any significant way, leaving its structure pristine and undisturbed. Isolation may even explain why Malin 1 stayed invisible for so long. Without nearby galaxies to interact with, there were no tidal streams, no merged star systems, and no gravitational lensing events to highlight its location. It simply drifted, quiet and unseen, relying on faint light and slow movement to tell its story. In a busier region, such a massive galaxy would have long ago been disturbed or altered into something more conventional, perhaps an elliptical galaxy or a distorted spiral filled with new stars. Instead, it remained pure, unrushed, a monument to what galaxies can become when they are left alone. The cosmic irony is striking. In a universe where everything seems to be in motion, shaped by interaction, tension, and violence, Malin 1 tells a different tale. A tale of solitude as a sculptor, of emptiness as a form of protection. Without the noise of neighbors, without the push and pull of galactic society, it quietly evolved into one of the largest and faintest spiral galaxies we've ever found. And yet, that same isolation may also be its curse. Without interaction, Malin may first never trigger the bursts of star formation that light up more active galaxies. It may never reach the brightness or complexity of its smaller, louder cousins. It may drift through the void for eternity, unchanging, unheard. A silent giant in a cosmic forest that no one walks through. But in that silence is something profound, proof that there are many paths to becoming a galaxy. That interaction isn't the only route to complexity. That grandeur doesn't require drama. Malin 1, massive and still, is a reminder that the universe rewards patience, and that some of its most extraordinary creations are shaped not by collision, but by cosmic peace. Malin 1's immense, ethereal disk and ghost-like spiral arms challenge not only our instruments, but our imagination. It doesn't behave like the galaxies we understand best, those forged in the heat of violence, sculpted by gravitational collisions, or born from rich cosmic neighborhoods. Its features ask an unsettling but thrilling question: did Malin 1 form differently? Is it the product of a cosmic pathway unlike any we've commonly modeled? The traditional framework of galaxy formation, what most of the cosmos seems to follow, suggests that galaxies grow hierarchically. Smaller structures merge to form larger ones. Gas falls into the gravitational grip of dark matter halos, condensing into stars, building up disks, forming bulges, feeding black holes. Most large spiral galaxies, like the Milky Way or Andromeda, are shaped by a series of mergers, accretions, and dynamic disturbances that drive star formation and structural evolution. But Malin 1 stands apart from this picture, and for decades now, astronomers have explored alternative scenarios to explain its bizarre nature. One leading theory is that Malin 1 formed through slow, prolonged gas accretion, a model in which gas from the intergalactic medium steadily trickled into a massive dark matter halo over billions of years. Instead of collapsing rapidly into a bright, compact disk, the gas was allowed to settle gently into an enormous, diffuse spiral, never reaching the densities needed for aggressive star formation. This would explain both the low surface brightness and the immense size. The galaxy simply accumulated material in a gradual, undisturbed process, with gravity quietly pulling hydrogen into a rotating disk that grew wider and wider over time. This slow accretion model fits beautifully with Malin 1's isolation. With no major interactions to disturb the inflow, and no nearby galaxies to inject angular momentum or compress gas, the galaxy could remain in a state of gravitational equilibrium, forming stars slowly, inefficiently, and spread thinly across its vast disk. Over time, this process would produce the exact features we observe today: faint spiral arms, a thin outer disk, and a large reservoir of untouched hydrogen. However, there's an alternative view. one that sees Malin 1 not as a galaxy that avoided chaos, but as one born of it, and then mysteriously stilled. In this model, Malin 1 might be the relic of a failed or incomplete galaxy merger. A major galactic collision, long ago, could have flung material outward, forming a massive disk-like structure of gas and stars, but for some reason, instead of collapsing into a compact elliptical galaxy as expected, the remnant remained spread out. Perhaps the conditions of the merger were unusually symmetric, or the colliding galaxies were extremely gas-rich and low-density themselves, leading to the formation of a massive but diffuse remnant. This scenario would suggest that Malin 1's current form is not primordial, but a result of a rare post-merger relaxation, a structure that stabilized after the chaos of impact and then faded into quietude. The sparse distribution of stars, the low metallicity, and the relatively calm kinematics of the galaxy today might all be aftershocks of an ancient, unusual collision, one that didn't ignite furious starbursts, but instead left behind a slow, sprawling ghost. Yet another intriguing possibility lies not in what happened to Malin 1, but in where and when it happened. Some astronomers have speculated that Malin 1 formed under special conditions in the early universe, perhaps inside a particularly massive and quiescent dark matter halo, in a region that never experienced the density fluctuations or tidal interactions necessary for a brighter galaxy to form. In this model, Malin 1's uniqueness is a cosmic fluke, a product of rare initial conditions that led to an unusually stable, under-illuminated spiral that managed to grow large without ever becoming bright. Such a hypothesis draws from the broader study of ultra-diffuse galaxies, UDGs, a class of galaxies that, like Malin 1, seem to challenge the standard correlation between size, brightness, and stellar density. UDGs are sometimes found in clusters, where environmental effects can strip or prevent star formation. But Malin 1 exists outside a cluster, possibly hinting at a new category altogether, one where the galaxy formed dark, remained undisturbed, and never converted much of its gas into stars. There's even been fringe speculation that Malin 1 might have formed from cosmic web filaments, slowly siphoning gas along the invisible strands of the large-scale structure of the universe. In this model, instead of being fed by local clouds or satellite mergers, the galaxy is connected to larger cosmic rivers of hydrogen that feed its disk over time, without the disturbances usually caused by local gravity wells. While this idea remains speculative and difficult to test, it offers a tantalizing image, a galaxy grown from the threads of the universe itself, slowly spun across billions of years. Each of these theories carries its own implications and problems. The slow accretion model explains much but struggles to account for the galaxy's surprisingly coherent spiral structure, which usually requires density waves or interactions to form. The failed merger model would need to have been extraordinarily gentle to result in a structure this undisturbed. The special conditions scenario leaves us wondering how often such initial environments could have occurred, and if they did, why don't we see more Malin 1s? And perhaps we do, perhaps we've missed them. Galaxies like Malin 1 are almost invisible to most of our surveys. Their surface brightness is below the detection threshold of many telescopes, meaning they could be hiding in plain sight, scattered across the sky like whispers among shouts. If so, Malin 1 might not be an anomaly, but the first known member of a vast hidden population, galaxies formed in quiet, in slow motion, under cosmic circumstances that favor subtlety over spectacle. Whatever the truth, one thing is clear, Malin 1 doesn't fit easily into any of our standard boxes. It challenges the default narratives of galactic growth. It whispers of processes slower, colder, and more delicate than those we usually study. And in doing so, it forces us to broaden our understanding, not just of how galaxies behave, but how they come to be. Malin 1 exists in a kind of cosmic solitude, not just as an isolated object in space, but as a galaxy defined by the emptiness around it. In the vast interconnected web of galaxies that make up the observable universe, most systems are deeply shaped by their surroundings, by the galaxies near them, the groups and clusters they orbit within, the filaments of gas they travel along, or the dense knots of dark matter that pull and twist their forms. But Malin 1's environment is strikingly empty. It floats through a region of space that is eerily quiet, and it is precisely this lack of neighbors that may be key to understanding its evolution. The local environment of a galaxy is one of the most powerful forces acting on its structure and destiny. Galaxies in dense environments, like clusters, are regularly subjected to interactions. They experience tidal stripping, ram pressure gas loss, gravitational harassment, and mergers. These processes can violently alter a galaxy's shape, quench its star formation, and fundamentally change its identity. Spirals become ellipticals, active regions go silent, and disks are shredded into diffuse arcs. But none of these marks are evident in Malin 1. Its form is not broken or misshapen. Its rotation is smooth, its spiral arms, though faint, are coherent, and its disk is wide but undisturbed. These clues point toward a life spent in relative isolation. Indeed, deep sky surveys around Malin 1 have found precious few neighboring galaxies of any substantial mass. There are no major galaxies close enough to have gravitationally influenced its formation or evolution in the way the Milky Way interacts with the large and small Magellanic Clouds. No nearby systems to have stirred its gas, distorted its disk, or triggered waves of star formation. This absence of nearby gravitational threats or companions suggests that Malin 1 has lived a life almost entirely untouched by the forces that commonly shape large galaxies. This raises an interesting possibility. Malin 1's extraordinary size and structure may be the direct result of the vacuum it inhabits. Without frequent close encounters or intergalactic collisions, its gas was able to settle into a disk with enormous radial extent. There was no nearby gravitational influence to pull it into a tighter, denser configuration. No mergers to dump additional stars into the core. No interactions to thicken or warp the disk. Its thinness, its diffuseness, and its stability are all signatures of a galaxy that has simply been left alone. However, its environment is not just a passive absence. Even in emptiness, the surrounding space carries subtle clues about what kind of evolution Malin 1 underwent, or didn't undergo. For instance, the intergalactic medium in its vicinity appears to be cooler and less dense than in richer cosmic environments. That means less friction, less gas compression, and fewer opportunities for intergalactic shockwaves to initiate star formation. This may explain why Malin 1, despite its enormous supply of hydrogen, has not ignited more brightly. It's never been agitated by its surroundings. There's also the matter of missing satellite galaxies. In standard cosmological models, large galaxies are expected to be orbited by many smaller satellites, galactic building blocks left over from the hierarchical process of growth. The Milky Way has dozens of such companions, and even more are theorized to be lurking unseen. But Malin 1 seems to lack a significant population of satellites, or at least, any that are luminous or massive enough to influence it visibly. This absence might mean that Malin 1's dark matter halo formed in a more isolated pocket of space, where fewer dense regions coalesced into separate galaxies. This scarcity of nearby satellites further reduces the likelihood of minor mergers, events that can slowly build up the mass and complexity of a galaxy. Without those mergers, Malin 1 never received the jostling or compression that would have increased star formation or altered its disk. Instead, its evolution appears to have been governed primarily by internal processes, unfolding over cosmic time scales without external nudges. There's another clue hiding in the galaxy's dark matter profile. Malin 1's rotation curve, which remains flat at extremely large distances from its center, implies a massive dark matter halo stretching far beyond its visible boundaries. This dark halo may have protected it against minor gravitational interactions, stabilizing its disk against the torques and warps that often result from even weak encounters. Combined with its quiet surroundings, this strong internal gravity may have helped it maintain its fragile, extended form. Still, this tranquility invites questions. Is Malin 1 a rare exception, or does it point toward a whole category of hidden giants, galaxies that formed in cosmic voids or on the outskirts of large-scale filaments, too dim to be seen, too untouched to be shaped by others? If galaxies like Malin 1 are common in these underdense regions, then our maps of the universe, built mostly from bright galaxies, could be missing a vast population of low-surface brightness behemoths, sculpted not by proximity, but by profound loneliness. Future telescopic surveys aimed at identifying these faint, extended galaxies could reveal more about the nature of Malin 1's environment. If astronomers find more giants like it in similar cosmic backwaters, we may finally begin to understand the environmental recipe that makes a Malin-class galaxy possible: a deep potential well from dark matter, a steady supply of gas, and billions of years without a single major gravitational nudge. In the end, Malin 1's surroundings, or lack thereof, are not just background details. They are part of its identity. Its emptiness defines it. In a universe where violence often drives beauty, Malin 1 is the product of cosmic peace, a slow, stately masterpiece painted in isolation, and still drifting through the silent void. The discovery of Malin 1 was like uncovering a secret cathedral in the middle of a dark, uncharted forest. Not just because it was vast and beautiful, but because it was invisible, camouflaged so thoroughly by the limits of our detection methods that it went unnoticed for decades. This naturally leads to a profound and unsettling question: could galaxies like Malin 1 actually be common? Are there hundreds, thousands, or even millions of similarly ghostly giants floating undetected through the universe, their light too faint, their structure too diffuse to appear in our brightest maps of the cosmos? The short and thrilling answer is maybe. To understand how this is possible, we have to reconsider how we've built our image of the universe. Most of our galaxy surveys, especially those conducted before the 21st century, were biased toward brightness. Instruments were designed to capture strong light sources, galaxies bursting with stars, active nuclei, luminous spiral arms, or energetic mergers. This led to a catalog of galaxies that, while rich and informative, represents only the tip of the cosmic iceberg. Enter the idea of low-surface brightness galaxies, or LSBs. Unlike high-surface brightness galaxies, which concentrate their light into tight, easily detectable structures, LSBs spread their luminosity thinly across a wide area. They may contain plenty of stars, but those stars are so sparsely distributed that the galaxy becomes almost indistinguishable from the background sky. Malin 1 is the ultimate expression of this category, a spiral galaxy whose disk extends hundreds of thousands of light-years, but is so faint that it blends into the cosmic wallpaper. Astronomers have long known that LSBs exist, but Malin 1 was the first to show that they could be truly massive. This discovery blew open the possibility that we've been missing an entire population of galaxies, not just small, diffuse systems, but colossal structures that rival, or even surpass the Milky Way in mass and size. And because these galaxies are difficult to see using traditional optical telescopes, they may vastly outnumber the luminous galaxies we're used to studying. In the years since Malin 1's discovery, astronomers have made efforts to hunt for more of these cosmic phantoms. Advanced surveys like the Sloan Digital Sky Survey (SDSS) have helped uncover a growing list of candidates, and more recently, studies using sensitive radio telescopes, like the Arecibo Legacy Fast ALFA Survey, (ALFALFA), and the Meerkat Observatory, have identified large, hydrogen-rich galaxies with very low stellar brightness. These systems often go unnoticed in visual bands but light up in the radio spectrum, where neutral hydrogen can be detected through its 21-centimeter emission line. These findings suggest that the universe may indeed be teeming with LSBs, galaxies that, like Malin 1, formed stars at an exceptionally slow rate and remain too dim for early surveys to catalog. Some may be small and faint, others could be massive and majestic. But the common thread is their elusiveness. It's not that they're not there, it's that we're only now learning how to look. But how common are they, really? This is where things become both exciting and speculative. Simulations of galaxy formation within large-scale cosmological models, such as those produced by the Millennium Simulation or Illustris, predict that dark matter halos of all sizes should be widespread. If that's true, then galaxies like Malin 1 could represent just one of many evolutionary pathways for these halos, particularly in low-density environments where gas settles slowly and star formation is inefficient. In other words, LSB galaxies may be the natural outcome of galaxy formation under quiet, undisturbed conditions that are more common than we once assumed. Some researchers have even proposed that LSB galaxies could be the dominant galactic population in the universe by mass, not in total luminosity, but in sheer number and in the dark matter they contain. That would radically alter our understanding of how mass is distributed throughout the cosmos. It would mean that much of the universe is shaped and influenced by massive, nearly invisible giants, silent architects of gravity that sculpt galaxy clusters, filaments, and voids from behind a veil. There's a deep irony here. For centuries, humanity has looked up at the night sky, fascinated by the glowing points and swirls of light. We've built entire cosmological models around what we could see. But now, the growing body of evidence suggests that what we've seen so far is only the brightest 10% of what actually exists. The rest, the dark, the diffuse, the faint, has been hiding in plain sight. To find them, we're going to need new kinds of eyes. Telescopes like the Vera C. Rubin Observatory, which will conduct the Legacy Survey of Space and Time, LSST, are designed to go deep, wide, and sensitive, capable of detecting extremely faint objects spread across large areas of sky. Similarly, future space-based infrared and radio observatories may pierce the cosmic veil even further, uncovering galaxies whose light has been redshifted or smeared out by time and expansion. And when we find them, if we find them, we may discover that Malin 1 is not an outlier, but a prototype. A pioneer. The first of a hidden dynasty of galactic giants that defy our expectations, that live in the margins, and that challenge everything we thought we knew about where and how galaxies form. We may also need to rewrite our cosmic census. If LSBs are as common as some models now suggest, they would significantly influence our understanding of baryonic matter distribution, dark matter halo occupation, and even the cosmic star formation history. They might explain anomalies in gravitational lensing surveys or the dark mass inferred in galaxy cluster studies. In a very real sense, these faint galaxies could be the missing puzzle pieces that reconcile observations with theory. And so we return to the question, could galaxies like Malin 1 be common? They could be everywhere, drifting silently through the darkness. Massively influential, but nearly invisible. Galaxies made not of light, but of gravity, gas, and patience. Galaxies that whisper, not shout. If so, the universe is not just more crowded than we imagined, it's more enigmatic, more hidden, and more hauntingly beautiful than we ever dared believe. Even in the golden age of observational astronomy, with orbiting behemoths like the Hubble Space Telescope peering deep into the cosmos, Malin 1 remains a challenge. It is so dim, so diffuse, and so sprawling that even Hubble, famous for capturing the intricate structures of galaxies billions of light-years away, struggles to do it justice. That's not because Hubble isn't powerful enough. It's because Malin 1 lies in a realm of visibility that is fundamentally different. It doesn't lack distance, it lacks surface brightness. And that subtle distinction makes all the difference. The Hubble Space Telescope was designed to excel in high-resolution imaging across optical and near-infrared wavelengths. It's perfect for resolving dense star clusters, mapping sharp spiral arms, unveiling active galactic nuclei, and peering into the distant universe where light has been stretched by the expansion of space. It's best when light is focused, when it's intense, directional, and plentiful. But Malin 1 offers no such light. Its brilliance is not concentrated in glowing cores or starburst knots. Instead, it is thinly spread over an area hundreds of thousands of light-years wide, like a faint mist across a cosmic windowpane. This is the defining characteristic of low-surface brightness galaxies. LSBs, their light is not weak in total, but it's diluted per unit area. If you could compress all of Malin 1's light into a small ball, it would be bright. But that light is smeared across a disk so vast, and so faint that its photons barely outshine the background noise of the universe. Hubble, for all its sensitivity, was simply not optimized to detect such large, faint structures. To be more precise, Hubble's instruments, particularly the Wide Field Camera 3 and earlier, the Advanced Camera for Surveys, have limitations when it comes to detecting low surface brightness features. These instruments can achieve phenomenal resolution, down to fractions of an arcsecond, But that resolution doesn't help when the thing you're trying to image is invisible against the backdrop of cosmic static. The camera's pixels are tuned to capture sharp contrasts and luminous edges. Malin 1, in contrast, is composed almost entirely of soft gradients, barely distinguishable from the background sky even in long exposures. Another problem lies in the background subtraction techniques used by many modern telescopes. In trying to remove noise, scattered light, and instrumental glare, the processing software can inadvertently erase the very thing it's trying to reveal. Faint outer disks like those in Malin 1 can vanish during image calibration, mistaken for noise or optical artifacts. This makes it difficult to detect the extended structure of the galaxy, even when you're looking directly at it. When Hubble did finally turn its lens toward Malin 1 in 2007, what it captured was a shock to many astronomers. The galaxy's central bulge and inner regions, previously thought to be a blurry, featureless mass, were revealed to contain a barred spiral structure, far more typical of familiar galaxies than anyone expected. This raised a new question: was Malin 1 truly exotic, or was it a normal galaxy hiding inside a halo of ghostly material? What became clear is that the inner 30,000 light-years of Malin 1 look surprisingly like an ordinary early-type spiral galaxy. It's only when you step back and examine the full extent of the disk, spanning over 650,000 light-years, that you see the full strangeness unfold. Hubble couldn't image the full disk clearly. It simply wasn't designed to. Its field of view was too narrow, its detectors too optimized for brilliance. It saw the heart of the ghost, but not its limbs. To study those limbs, those impossibly faint arms that stretch far beyond the norm, astronomers have had to turn to ground-based telescopes with wide-field cameras, and even more importantly, to radio observatories that detect hydrogen rather than light. Instruments like the Very Large Array, VLA, and the Arecibo Observatory have been able to trace the distribution of neutral hydrogen gas in Malin 1, confirming that the galaxy's mass and structure extend well beyond what Hubble could see. Still, the challenge persists. Even with powerful modern instruments, fully resolving Malin 1 in all its ghostly grandeur is a formidable task. Its brightness is estimated to be below 25 magnitudes per square arc second, an extraordinarily faint level that hovers right at the edge of detectability for most optical systems. The galaxy does not announce itself. It whispers softly, at the limits of perception. But this isn't just a technical problem, it's a philosophical one. Malin 1 reminds us that the universe is not just filled with bright things. It is also filled with hidden things, things that evade our most advanced instruments not because they are too far, but because they are too gentle, too soft, too subtle to scream through the cosmic static. This limitation has profound implications for galactic astronomy. If Malin 1 is difficult to detect even with Hubble, what about the thousands of similar galaxies that might be even fainter? How many are hiding in archival data, dismissed as imaging artifacts or buried beneath software thresholds? And how many more have gone completely undetected, waiting in the darkness for new generations of telescopes to see what Hubble could not? The answer may lie with future observatories, particularly those designed with low surface brightness sensitivity in mind. The Vera C. Rubin Observatory, the upcoming Nancy Grace Roman Space Telescope, and even specialized balloon and satellite-based wide-field instruments may soon break through the optical fog, revealing galaxies that exist below the radar of traditional techniques. Until then, Malin 1 stands as a monument to the limits of perception. Not because it's too far. Not because it's too small. But because it dares to exist between the thresholds of visibility, mocking the boundaries we once believed were universal. While optical telescopes struggled to bring Malin 1 into focus, radio telescopes provided a different kind of vision, one not based on the shimmering starlight we usually associate with galaxies, but on something deeper, more fundamental, and far more revealing, the faint radio whispers of hydrogen. Where the eye fails, the ear of the cosmos listens, and in Malin 1's case, that listening revealed a sprawling, massive disk soaked in neutral hydrogen gas, stretching farther than almost any spiral galaxy known. Radio astronomy didn't just confirm Malin 1's existence, it rescued it from obscurity, placing it on the map of cosmic structure in a way optical observations alone never could. The key lies in the 21-centimeter hydrogen line, a spectral signature emitted by neutral hydrogen atoms when the spins of the proton and electron flip relative to each other. This process is rare on a per-atom basis, but because hydrogen is the most abundant element in the universe, especially in the vast interstellar and intergalactic medium, this radio emission becomes a powerful tracer of cold gas reservoirs across galaxies. And in Malin 1, it told a staggering story. This ghost galaxy, nearly invisible in visible light, is rich in hydrogen, possessing a disk that goes well beyond its already massive optical footprint. Early radio observations using instruments like the Very Large Array, VLA, and Arecibo Observatory were crucial in defining the true scale and structure of Malin 1. The radio emissions revealed that the galaxy's neutral hydrogen disk extends out to roughly 120 arcseconds on the sky, over 650,000 light-years in actual spatial size, dwarfing the Milky Way and placing Malin 1 among the largest known spiral galaxies by diameter. The gas was not simply drifting in isolation either, it was rotating, and doing so in a flat, orderly fashion that mimicked the motion of more compact spiral galaxies. This meant Malin 1 wasn't just a loose collection of material, it was gravitationally bound, stable, and massive. What made these radio observations especially significant was that they allowed astronomers to measure the rotation curve of Malin 1 far beyond its visible boundaries. By examining the Doppler shifts of the 21 centimeters emission at different radii, scientists could track how fast the gas was orbiting the galactic center. The result? A rotation speed that remained high and flat even in the galaxy's outermost regions with almost no visible stars. This was one of the earliest and clearest indications that Malin 1's mass was not where its light was. The stars we could see only accounted for a tiny fraction of the total gravitational influence. The rest was dark. This phenomenon, called the rotation curve problem, had already been observed in other galaxies and was a foundational piece of evidence for dark matter. But in Malin 1, it was taken to the extreme. Its rotation speeds demanded a massive dark matter halo, far larger than those of typical spiral galaxies, and that halo had to extend across a disk that was nearly invisible in optical wavelengths. The hydrogen gas provided the only traceable substance to confirm its shape. More radio observations continued to build the picture. Studies using radio interferometers allowed astronomers to map the hydrogen distribution in greater detail, revealing not only the extent of the disk but subtle features within it, regions where gas density was slightly higher, possible remnants of small-scale interactions or ancient internal perturbations. But overall, the disk was calm, coherent, and shockingly symmetric. There were no tidal tails, no warps, no signs of major past collisions. This was a galaxy formed and governed by quiet processes, and its gas had remained largely undisturbed for billions of years. Importantly, these radio studies also helped answer a key question. Why was Malin 1 so faint despite being so massive? The answer was hiding in the balance between gas and stars. While hydrogen was abundant, star formation was weak. The gas had never collapsed into dense clusters sufficient to form large numbers of luminous stars. It remained in a state of low density, cold but widespread, spiraling slowly around a dark core that itself was largely hidden from view. The galaxy had the fuel, but for some reason, the ignition never came. Radio telescopes didn't just illuminate the scale of Malin 1, they redefined its classification. Thanks to its hydrogen signature, astronomers began to recognize it not merely as an optical oddity but as a gas-dominated, low-surface brightness giant, part of a growing class of galaxies that exist primarily in the radio spectrum. In fact, radio surveys began uncovering other Malin-like systems, previously invisible in visible light, suggesting that Malin 1 might not be a lone anomaly, but a prototype of a broader, hidden population. This has shifted the strategy of future galactic surveys. Now, astronomers are placing greater emphasis on multi-wavelength observations, combining optical, infrared, and radio data to uncover galaxies that may be invisible in one part of the spectrum but clearly defined in another. For Malin 1, this synergy is crucial. The visible light tells us where stars are. Infrared reveals the older, cooler stars. But radio? Radio shows us where the raw material for future stars lies, and how it moves through the gravitational architecture of the galaxy. And Malin 1's radio signals continue to whisper across the void, offering more to study. Ongoing and future observations using facilities like the Square Kilometre Array, SK, will bring even greater sensitivity and resolution to the study of LSB galaxies. These next-generation arrays may detect faint companions, extended gas structures, or even cold gas inflows that have so far eluded detection. They may uncover the slow accretion patterns that built Malin 1's enormous disk over billions of years. Without radio astronomy, Malin 1 might still be a faint blur on a photographic plate, misclassified or entirely forgotten. It was radio telescopes that allowed us to see through the veil, revealing not only its shape and size but the hidden skeleton of mass and motion beneath its barely visible skin. They taught us that galaxies don't have to shine to be enormous. That mass can move in silence. That gravity leaves fingerprints even where light does not. And so, as the radio waves continue to reach us from this distant giant, waves that left Malin 1 nearly 1.2 billion years ago, they carry with them the heartbeat of a galaxy that is not loud, but lasting. A galaxy that whispers, across eons, in the quiet language of hydrogen and darkness. Malin 1's journey from obscurity to astronomical fascination didn't end with radio telescopes. While they were essential in revealing its massive hydrogen-rich disk, a clearer picture of this ghostly giant's structure and vast dimensions would come through the precise, methodical gaze of one of the most ambitious digital sky mapping projects in history, the Sloan Digital Sky Survey, or SDSS. Launched in 2000, SDSS marked a revolution in observational astronomy. Instead of relying solely on photographic plates or narrow surveys of small regions, SDSS set out to systematically image and spectroscopically map large swaths of the sky with unprecedented depth, resolution, and consistency. Mounted on a 2.5-meter telescope at Apache Point Observatory in New Mexico, and equipped with advanced CCD detectors, the survey collected data in 5 optical bands U, G, R, I, and Z, spanning ultraviolet to near-infrared. It provided not only images, but detailed spectra of millions of celestial objects, helping to determine distances, redshifts, compositions, and more. For a galaxy like Malin 1, which had already eluded visual confirmation for decades, SDSS provided a much-needed second look, and more importantly, a digital one. Unlike traditional photographic surveys, SDSS didn't suffer from the same limitations in detecting faint, extended features. Its CCD detectors were more sensitive to low surface brightness, and its digital pipeline allowed astronomers to analyze light profiles and spatial structure with precision unavailable in previous eras. When SDSS turned its focus toward the region of sky containing Malin 1, it added critical data that confirmed and refined our understanding of the galaxy. First, it helped better constrain the morphology of Malin 1. While Hubble had provided a high-resolution view of its inner region, revealing a barred spiral core, SDSS provided a broader context. It showed that the galaxy's faint outer disk, barely perceptible in previous imagery, extended much farther than previously confirmed, aligning well with what radio telescopes had indicated through hydrogen mapping. Using SDSS's multiband imaging, astronomers were able to perform surface brightness profile analyses, essentially measuring how the brightness of Malin 1 changes as you move outward from the center. These profiles confirm that the galaxy's luminosity falls off extremely gradually with radius, far more slowly than in typical spiral galaxies. This is a hallmark of low surface brightness structure. Instead of dropping off sharply, the light lingers faintly at great distances, barely detectable above the sky background. Moreover, by analyzing the color gradients across Malin 1, SDSS data helped distinguish between regions dominated by older, redder stars and areas that might contain younger, bluer populations. The results painted a picture of a galaxy that had seen very little recent star formation, consistent with earlier radio findings that showed a huge gas reservoir largely untouched by stellar ignition. Malin 1 wasn't just faint, it was old and quiet, with most of its stars likely formed long ago in a gentle, slow process. Perhaps most importantly, SDSS provided a reliable redshift measurement based on spectroscopic data from Malin 1's central region. From this, astronomers refined the galaxy's distance to about 1.19 billion light-years, placing it firmly in the cosmic neighborhood of the Coma Berenice's constellation. With distance and angular size known, the physical dimensions of the galaxy could be recalculated with greater confidence. The result? A confirmed disk diameter of at least 650,000 light-years, and potentially more if faint outskirts extend even further than current observations suggest. This measurement made it official. Malin 1 is one of the largest spiral galaxies ever discovered, over 6 times the diameter of the Milky Way. And thanks to SDSS, this wasn't speculative. It was anchored in hard photometric and spectroscopic data. What had once been a mysterious smudge on a photographic plate was now clearly resolved, digitally catalogued, and studied in detail. The data also contributed to theoretical models. Armed with SDSS's detailed surface brightness data, researchers could better model the mass-to-light ratio of Malin 1. That is, how much unseen mass, likely dark matter, is needed to account for the observed dynamics of such a faint galaxy. The results were striking. The visible matter in Malin 1, even stretched across its enormous disk, was insufficient to explain the galaxy's rotation curve. The need for a massive dark matter halo became even more compelling. Additionally, SDSS helped reveal something subtle but telling about Malin 1's symmetry and stability. Its extended spiral arms, faint though they were, showed remarkable coherence, forming graceful, loosely wound arcs far from the core. This indicated that Malin 1 was not a chaotic or disrupted system, but one that had retained its structural identity over billions of years. Its symmetry, in a sense, was a story of its loneliness and stability, untouched by major galactic mergers, unshaken by violent tidal forces, and preserved in its original elegance. But perhaps the most important insight SDSS gave us was context. Because the survey wasn't just about individual objects, it was about relationships. By mapping the positions and redshifts of millions of galaxies, SDSS allowed astronomers to locate Malin 1 within the broader cosmic web. It showed that Malin 1 resides in a relatively underdense region, far from the rich clusters where galaxy interactions are frequent. This solitude was not anecdotal, it was measurable, quantifiable, and cosmologically relevant. Malin 1's isolation wasn't a fluke. It was likely a key factor in its development. The success of SDSS in revealing these aspects of Malin 1 also inspired renewed interest in searching for other ultra-diffuse and LSB galaxies. If one such massive system had gone unnoticed for so long, how many others might be lurking in the data, waiting to be pulled from the shadows by the same methods? In fact, SDSS data has already led to the discovery of a number of ultra-diffuse galaxies, UDGs, particularly in galaxy clusters like Coma, where they appear as large as the Milky Way but contain only a fraction of its stars. These discoveries suggest that Malin may first not be alone. It may be the brightest whisper in a chorus of cosmic ghosts, stretching across the sky, waiting for us to listen closely enough to hear them. In many ways, SDSS transformed Malin 1 from a curiosity into a template. It gave astronomers the tools to measure, model, and compare, to place this ethereal object within the hierarchy of galactic formation and evolution. And it reminded us that in the age of digital astronomy, what we can see is not just what shines, but what we know how to look for. Thanks to SDSS, Malin 1 is no longer just the galaxy that defied detection. It is the galaxy that helped redefine detection itself. The story of Malin 1 is far from over. In many ways, it has only just begun. While earlier generations of instruments like Hubble, Arecibo, and the Sloan Digital Sky Survey gave us glimpses into its enormous structure, massive gas disk, and dark matter dominance, there's still much we don't understand about how it formed, how it evolved, and what exactly is lurking within and around it. But now, with a new generation of telescopes either active or soon to be operational, we are standing at the brink of an observational renaissance. These instruments may finally bring Malin 1 fully into focus, not just its ghostly face, but its inner secrets. At the forefront of this effort is the James Webb Space Telescope, JWST, a marvel of modern engineering and arguably the most sensitive infrared observatory ever constructed. While JWST was not specifically designed to study low-surface brightness galaxies, its unique capabilities could make it one of the most important tools for studying galaxies like Malin 1. Why? Because infrared light is less affected by dust, better at penetrating diffuse environments, and capable of revealing older, redder star populations that form the structural backbone of extended galaxies. For Malin 1, JWST's ability to observe in the near and mid-infrared could be revolutionary. It could peer into the outer disk, where faint older stars, the remnants of slow star formation over billions of years, still drift in the dark. It could also reveal whether embedded stellar clusters or hidden star-forming regions exist within the hydrogen-rich regions identified by radio telescopes, but previously invisible in optical bands. These dusty, cold regions may still be nurturing stars too young and faint to shine through invisible light, but in the infrared, JWST may detect their thermal glow. More intriguingly, JWST might be able to detect globular clusters or satellite dwarf galaxies in Malin 1's halo. These components can act like galactic fossils, telling us about a galaxy's formation history through their orbits, ages, and compositions. If Malin 1 possesses a system of globular clusters, that would imply a more complex and ancient formation than we currently assume. If it lacks them, that would support theories of a slow, isolated evolution in a quiescent region of space. But JWST is only one part of the future. Another critical tool will be the Nancy Grace Roman Space Telescope, scheduled for launch later this decade. Roman will offer a wide field of view, much wider than JWST or Hubble, combined with Hubble-level resolution. This makes it perfect for imaging extremely large, faint structures, like Malin 1's diffuse spiral arms, in a single frame. Roman could be the first telescope to image the full extent of Malin 1's disk with high resolution, from its bright core to the edge of its ghostly limbs. Its sensitivity and sky coverage also make Roman ideal for conducting surveys aimed specifically at uncovering more ultra-diffuse galaxies, potentially identifying dozens or hundreds of Malin 1 analogs. These discoveries would allow comparative studies. Is Malin 1 truly unique, or just the brightest member of a hidden population? Meanwhile, on the ground, telescopes like the Vera C. Rubin Observatory are preparing to begin their mission. With its legacy survey of space and time, LSST, Rubin will scan the entire southern sky repeatedly over 10 years, building up deep, time-resolved images of billions of objects. Rubin's cameras are optimized for detecting extremely faint, extended features, exactly the kind of structures that define Malin 1 and its kin. What Rubin brings is scale. It won't just study Malin 1, it could find the rest of its family. And by comparing hundreds or thousands of LSB galaxies, astronomers may finally be able to answer the question, is Malin 1 an anomaly, or a tip of an iceberg we've only begun to uncover? In the radio domain, the upcoming Square Kilometre Array, SKA, will dramatically improve sensitivity and resolution for neutral hydrogen mapping. SKA will be able to trace hydrogen structures out to redshifts beyond 1, and in galaxies far fainter than what current observatories can handle. For Malin 1, SKA could map the hydrogen distribution across the entire disk in exquisite detail, potentially detecting gas inflows, warps, turbulence, or even dark satellite companions that are invisible in every other wavelength. It could also answer one of the most lingering questions: is Malin 1 still accreting cold gas from the intergalactic medium? If so, that could explain how it sustained such a vast hydrogen supply without undergoing significant star formation. SKA could watch this process in real time, measuring how gas settles into the disk and how it's redistributed by rotation, turbulence, or even faint feedback processes. And then there's the possibility of detecting gravitational lensing effects from Malin 1's dark matter halo. While it's located in a relatively empty region, high-precision astrometry from missions like Gaia, combined with next-gen deep sky surveys, may reveal subtle distortions in background light, telling us more about the shape and concentration of its dark matter distribution. Even artificial intelligence and machine learning will play a role. With such vast data sets pouring in from Roman, Rubin, SKA, and other instruments, traditional methods of image analysis will no longer be fast or sensitive enough. AI systems trained to recognize the unique signatures of low surface brightness structures will help sift through the data, highlighting candidates for deeper study, and perhaps even finding Malin 1-like systems in places we'd never think to look. But perhaps the most exciting prospect is what we don't yet anticipate. Every time we've gained access to a new window of the electromagnetic spectrum or developed a more sensitive instrument, we've discovered things we didn't even know to look for. The same could be true of Malin 1. JWST, Rubin, Roman, SKA, these tools may not just refine our knowledge of this galaxy. They may rewrite it. They may show that Malin 1 isn't just a faint, diffuse oddity, but a puzzle piece in a larger story about how galaxies form, grow, and survive in the quiet corners of the universe. We may discover that Malin 1 holds ancient scars from long-past interactions, visible only in far-infrared or ultraviolet. We may uncover ultra-cold molecular gas deep in its core. We may detect a dormant supermassive black hole at its heart, never before noticed. Or, perhaps most humbling of all, we may find that Malin 1 is merely average in a population that has gone unnoticed for the entire history of observational astronomy. In the coming years, as data from these observatories streams in, our picture of Malin 1 will evolve from a ghost into a living entity. An entity with complexity, history, architecture, and behavior. A galaxy not merely known, but understood. A galaxy that has waited over 1 billion years for us to finally have the tools, patience, and vision to see it for what it truly is. Studying faint giants like Malin 1 is an endeavor at the very edge of observational astronomy. These are not just big galaxies. They are ghostly giants, colossal in size but nearly invisible due to their extreme low surface brightness. The challenge isn't that they're far away, though they often are, it's that their light is too diffuse. Spread thinly over enormous areas, their photons are few and far between, often drowned in the sea of background noise that fills every astronomical image. Detecting such objects is like trying to spot a single wisp of fog drifting across a foggy landscape using a flashlight that only illuminates bright spots. The fundamental issue is that our telescopes and detectors are not built to favor the faint and extended. Most astronomical instruments are designed to pick up point sources, bright stars, quasars, compact galaxies, things that deliver a concentrated burst of light into a small patch of the sky. Even when imaging large galaxies, our equipment tends to work best when those galaxies are relatively bright and well-defined. Malin 1 and galaxies like it are the opposite, large, diffuse, and faint in almost every wavelength. Their very nature works against the tools we've historically built. One of the biggest hurdles in detecting faint giants is the problem of sky background. The universe is never truly dark. Even in space, the sky has a background brightness due to zodiacal light, scattered starlight, instrument noise, and even residual airglow in ground-based observations. For most bright objects, this background is negligible. But for galaxies like Malin 1, where the surface brightness drops below 25 to 28 magnitudes per square arc second, the object itself can be almost indistinguishable from the background. This means a significant amount of data processing is needed just to separate the signal from the noise, a process that is both sensitive and prone to errors. And here's where the technical challenges pile up. Astronomers use a process called background subtraction to remove the noise from astronomical images. This works well for small, compact objects. But when a galaxy is extremely large and faint, its extended light is often mistaken for background and accidentally subtracted out during the processing stage. This leads to false negatives, giant galaxies that are effectively erased by the very software designed to find them. Another issue lies in dynamic range. Most detectors have to balance the ability to image bright objects without saturation and faint objects without losing detail. In the case of faint giants, the inner core of a galaxy, like Malin 1's central bulge, may be much brighter than the outskirts. To properly capture the faint outer regions, very long exposure times are needed. But during long exposures, even small tracking errors, cosmic rays, or changes in atmospheric conditions, for ground-based telescopes, can introduce artifacts that obscure or distort the already faint signal. Telescope field of view is also a limiting factor. Malin 1 is over 650,000 light-years across, which translates to a relatively large angular size on the sky even though it's 1.2 billion light-years away. Many high-resolution telescopes, like Hubble, have narrow fields of view. While they excel at zooming in on tight structures, they can't capture the full spread of a giant galaxy like Malin 1 without stitching together multiple images. This mosaic process is time-consuming and complex, and even then, the stitching process itself can introduce further background subtraction problems that artificially diminish the extended halo. Then there's the issue of wavelength coverage. Malin 1, like many low-surface brightness galaxies, emits weakly in the optical but may be more visible in the radio, infrared, or ultraviolet. A single telescope, even a powerful one, rarely covers the full electromagnetic spectrum. This means astronomers must combine data from multiple observatories: radio for mapping hydrogen, infrared for detecting old stars, UV for catching glimpses of rare young stars. But coordinating observations across such a wide range of instruments is complex, and the data integration process is extremely delicate. Compounding all of this is the human factor, our own expectations and biases. For decades, galaxy surveys focused on what was easiest to see. This created a kind of observational bias, a tendency to search for, and thus find, galaxies that matched our preconceived notions of what galaxies should look like. Malin 1 shattered those notions. It showed that galaxies could be vast, diffuse, and nearly transparent. But even now, many automated search algorithms are not well tuned to detect such outliers. They're trained to look for bright, concentrated structures. As a result, we may still be missing galaxies that don't fit the pattern. To make matters even more intricate, observing faint giants requires extremely dark skies. Even the best ground-based telescopes, located on mountaintops far from city lights, suffer from residual light pollution and atmospheric scattering. That's why future detection efforts increasingly look to space-based telescopes, away from Earth's interfering glow. But these come with their own challenges: high cost, limited time allocation, and restricted wavelength flexibility. There's also the challenge of cosmic dimming. The surface brightness of extended objects diminishes with the square of the redshift due to the universe's expansion. Malin 1, at 1.2 billion light-years away, is already affected by this. But galaxies even farther out, if they're also LSB types, may be beyond the detection threshold entirely, even for our most sensitive instruments. Yet despite all these challenges, technology is advancing. New detectors with lower noise levels, larger fields of view, and better background subtraction algorithms are being developed. Artificial intelligence and machine learning are being trained to identify diffuse structures with far greater sensitivity and fewer false positives. Multi-wavelength surveys are becoming more seamless, allowing us to cross-reference data from radio, infrared, and optical regimes with greater ease. The Verisi Rubin Observatory is designed with many of these challenges in mind. Its legacy survey of space and time, LSST, will collect extremely deep, wide-field data, capturing the full extent of faint structures like those in Malin 1 over long timescales. Coupled with advances in data processing, it promises to uncover not just individual LSB giants, but a statistical sample, enough to finally answer whether Malin 1 is rare or just the first we've found. In the end, the difficulty of studying faint giants is a reminder that the universe is not limited by our perceptions. The cosmos is vast, subtle, and often quiet. Galaxies like Malin 1 challenge us not with their violence or brilliance, but with their stillness and silence. They require patience, ingenuity, and above all, humility. A recognition that much of the universe may be hidden not because it is far, but because we have not yet learned how to see it. When Malin 1 was first identified, it seemed like a strange anomaly, a massive spiral galaxy unlike anything seen before. But as astronomers delved deeper into its nature and sought out similar structures, a revelation began to take shape. Malin 1 wasn't just an oddball. It was a trailblazer, the first confirmed member of what would eventually become known as a new class of galaxy, the ultra-diffuse galaxies, or UDGs. Ultra-diffuse galaxies are strange creatures of the cosmos. They can be as large as the Milky Way in terms of spatial extent, yet contain only a fraction of the stars, sometimes just 1% or less. Their surface brightness is so faint that for decades, they were systematically missed by traditional surveys. They aren't just dim, they are ethereal, spread thin across hundreds of thousands of light years, resembling more of a galactic phantom than a conventional stellar city. Malin 1, with its vast disk, ghostly arms, and nearly invisible halo, was the prototype for this overlooked population. The realization that Malin 1 was not alone came slowly. In the decades following its discovery, astronomers began uncovering more and more galaxies that shared similar traits: large diameters, low star formation rates, enormous reservoirs of hydrogen gas, and extremely low surface brightness. But it wasn't until the 2010s, particularly with deep sky surveys in regions like the Coma cluster, that the true population explosion of UDGs became apparent. Coma, a dense galaxy cluster located about 320 million light-years away, became the hunting ground for some of the most dramatic discoveries in this field. Using telescopes like the Dragonfly telephoto array, a novel instrument optimized for detecting diffuse light, astronomers identified hundreds of ultra-diffuse galaxies in the cluster. Many of them were comparable in size to the Milky Way but possessed far fewer stars, barely enough to form a discernible spiral or elliptical structure. Others were even larger, with halos stretching into megaparsec scales, but composed of ancient, dim, red stars, fossils of a long-dormant stellar past. These discoveries were profound. They suggested that the cosmos may contain a vast hidden population of galaxies, invisible not because of their distance, but because of their intrinsic faintness. The universe, we began to realize, was not just filled with bright spirals and compact ellipticals. It was also woven with a shadowy network of galactic ghosts, like Malin 1, drifting quietly in the void. What made these galaxies even more interesting was their diversity. Some UDGs were found to be gas-rich, like Malin 1, still retaining significant hydrogen supplies and rotating in orderly, disk-like fashions. Others were completely gas-poor, appearing more like ancient relics that had long since exhausted or lost their fuel for star formation. This diversity hinted at multiple formation pathways. Some UDGs might be failed galaxies that never successfully ignited starburst phases. Others might be stripped-down survivors of violent encounters, having had their gas and stars siphoned off by interactions with larger galaxies or the harsh environments of dense clusters. Malin 1's role in this was foundational. Its very existence showed that a galaxy could be enormous, dark matter-dominated, gas-rich, and almost completely invisible in optical light. It set the precedent that such systems could form and survive in relatively isolated environments. When UDGs were later found in clusters, astronomers began to consider whether there might be two evolutionary tracks, one for cluster UDGs formed through tidal interactions and environmental stripping, and another for field UDGs, like Malin 1, that developed slowly and quietly in the cosmic outskirts. In this light, Malin 1 became more than just a curiosity. It became a cosmological laboratory, a case study in how galaxies could evolve without violence. Its rotation curve, low stellar density, extended disk, and massive dark matter halo were all clues pointing toward a mode of galaxy formation previously overlooked by the high brightness bias of earlier surveys. It showed that galaxies didn't need to shine brightly to be massive or significant. Further studies of UDGs revealed another intriguing detail. Some of them have unusually large globular cluster systems. This was unexpected because globular clusters are typically associated with massive galaxies. Yet these ghost galaxies, with so few stars, sometimes harbored tens or even hundreds of ancient globulars. This mismatch between total stellar mass and globular cluster populations suggested a hidden truth, that many UDGs are massive in terms of total halo mass, even if they appear insignificant in visible light. Malin 1, again, fits this mold. Though direct studies of its globular cluster population are still limited due to its extreme faintness and distance, its flat, extended rotation curve already tells us that it possesses an enormous halo of dark matter, one consistent with galaxies many times more luminous. This reinforces the idea that luminous mass is not always a good tracer of total mass in the universe. Some of the most massive structures may, paradoxically, be among the hardest to detect. The study of ultra-diffuse galaxies also raises deep theoretical questions about galaxy formation models. In standard lambda cold dark matter cosmology, galaxies form as baryonic matter falls into dark matter halos. Feedback from star formation and supernovae then shapes how visible matter accumulates. But if galaxies like Malin 1 can form and grow massive halos without corresponding amounts of star formation, that suggests alternative feedback mechanisms or unusual initial conditions may play a larger role than previously thought. Simulations are beginning to catch up. High-resolution models that incorporate detailed feedback processes, gas accretion, and environmental effects are now able to produce galaxies with UDG-like properties. Some of them arise from low-density gas accretion, leading to extended, low-efficiency star formation over billions of years. Others result from gas stripping in clusters, where galaxies are puffed up and dimmed by violent interactions. In both cases, the models match what we now see in galaxies like Malin 1. And yet, Malin 1 remains an outlier among outliers. It is one of the largest, most gas-rich, and most extreme LSB galaxies ever confirmed. Its very presence keeps pushing the boundaries of what we think galaxies can be. Its combination of enormous scale, spiral structure, low star density, and quiet rotation doesn't neatly fit into any one model. It straddles the definitions, spiral but ghostly, massive but nearly empty, ancient but unperturbed. As more UDGs are discovered, Malin 1 will serve as a benchmark, a standard by which others are measured. It will help determine which UDGs are likely isolated giants, and which are battered remnants. It will shape how astronomers distinguish between different formation channels. And it may even help uncover new types of dark galaxies, systems so devoid of stars that only their gravitational pull gives them away. Perhaps one day, Malin 1 will no longer be considered exotic. Perhaps future surveys will reveal thousands like it, each whispering a different chapter in the quiet story of the cosmos. But whether common or rare, Malin 1's importance lies in what it revealed, that the universe is not just a place of fireworks and brilliance, but also a place of shadows, subtlety, and scale beyond anything we imagined. Malin 1 didn't just expand our catalog of known galaxies. It fundamentally redefined what astronomers thought galaxies could be. Before its discovery, most models of galaxy formation were biased toward the bright and the obvious. Galaxies were thought of as massive assemblies of stars with dense, glowing cores and structured, luminous arms, objects that stood out easily against the dark backdrop of space. But Malin 1, with its vast diameter, sparse stellar population, and ghostly appearance, forced astronomers to confront a troubling realization. Our view of the universe was incomplete, filtered not by reality, but by the limits of our detection tools. This revelation shifted the paradigm. Suddenly, it was no longer safe to assume that the visible universe was representative of the universe as a whole. Malin 1 became the poster child for what was lurking just below our observational threshold, a cosmos teeming with low surface brightness, LSB, structures that had gone undetected not because they were rare, but because we hadn't been looking for them properly. The implications of this shift were profound. For one, it challenged the completeness of existing galaxy surveys. Astronomers began to question the accuracy of large-scale structure maps, luminosity functions, and galaxy classification systems. If objects like Malin 1 could exist unnoticed for so long, how many others had we missed? And more importantly, how did their existence skew our understanding of galaxy evolution and the distribution of matter in the universe? Malin 1 also highlighted the critical role of dark matter. Unlike luminous galaxies where starlight and gas dominate the dynamics, Malin 1 showed that a galaxy could be dominated by dark matter to such a degree that its visible components were just the tip of a massive, invisible iceberg. This reinforced the idea that to truly understand galaxies, one must study their gravitational effects, not just their light. Moreover, the discovery of Malin 1 pushed astronomers to develop new observational techniques, better instruments, and smarter data processing algorithms. It encouraged innovation. Telescopes like Dragonfly, surveys like LSSD, and tools like AI-enhanced image recognition owe their rationale, in part, to the challenges Malin 1 presented. In every way, Malin 1 was a quiet revolution, not bright, but illuminating. It didn't shout its presence across the sky, but whispered a cosmic truth: the universe is more than meets the eye. If Malin 1 taught us anything, it's that the cosmos might be far richer, and far stranger, than what our eyes can easily detect. For decades, astronomy focused on what was most visible: the brilliant spirals, the compact ellipticals, the dazzling starbursts. But the emergence of Malin 1 and its kin has sparked a provocative and thrilling question: what if the universe is actually dominated by galaxies we can barely see? It's not just poetic speculation, it's a legitimate scientific possibility. Galaxies like Malin 1 are defined by their extremely low surface brightness, which means the light from their stars is spread thinly over such a large area that it fades into the cosmic background. If our instruments had never improved beyond the photographic plates of the early 20th century, Malin 1 and countless others like it would still be invisible. Which leads to a chilling realization: our historical census of galaxies has likely been incomplete. Low surface brightness galaxies, LSBs, especially ultra-diffuse galaxies, UDGs, are increasingly being found in surveys not because they suddenly appeared, but because we finally learned how to look for them. If that trend continues, we may soon find that these ghostly giants are not rare exceptions, but a dominant, hidden majority. In some cosmic neighborhoods, particularly in galaxy clusters like Coma or Virgo, UDGs already appear to rival or exceed the number of traditional, high-brightness galaxies. Now imagine extrapolating that to the entire observable universe. For every bright spiral glowing in the night sky, there could be dozens of massive, ancient, dimly lit galaxies drifting in silence. Their combined mass, especially if they're dark matter dominated like Malin 1, could represent a substantial portion of the universe's matter budget, matter that we've previously underestimated or missed entirely. This idea doesn't just change galaxy catalogs. It challenges how we model structure formation, galactic feedback mechanisms, and even the distribution of dark matter across the cosmos. If these galaxies formed under different conditions or evolved more quietly than their luminous counterparts, they might preserve the cosmic environment of the early universe better than anything else we've found. Malin 1 might be the first whisper of a cosmic chorus we've only just begun to hear. They drift where silence is older than time, where galaxies are born not with fireworks, but with whispers. Malin 1 is not merely a galaxy, it is a ghost. And like all ghosts, it reminds us of the unseen, the half-forgotten, the great and powerful presences that exist beyond the threshold of human perception. It is a story not told in light, but in absence, a cosmic ghost story etched into the dim canvas of the universe. Imagine standing beneath a dark sky, staring up into the abyss, and knowing that even in the blackest patch where no stars twinkle, there may lie a colossus, a galaxy larger than the Milky Way, older than our solar system, moving in silence and grace. It does not blaze with stellar fury. It does not announce itself with supernovae or brilliant clusters. Instead, it hangs there, content to fade, its light stretched thin across 100,000 parsecs, like fog rolling through the galactic night. Galaxies like Malin 1 are reminders that brightness is not the same as significance. Just because something doesn't shine doesn't mean it lacks substance. In fact, it may be the very opposite. Malin 1 has mass, great mass. It has motion, form, structure. And more than anything, it has patience. It waited over 1 billion years for its light to reach us, then waited even longer for that light to be recognized, studied, and understood. It makes you wonder, how many giants have passed us by unseen, unrecorded? How many cosmic ghosts roam the void, carrying within them histories we've never read, mysteries we've never asked, and lessons we've never considered? The universe could be full of them. Each one a quiet monologue in a drama that rarely needs an audience. They are the hidden architecture of the cosmos, building blocks of structure without fanfare or radiance. Their halos of dark matter shape the paths of surrounding galaxies. Their faint hydrogen tails stretch through intergalactic space like wisps of breath in a cold wind. Their ancient stars orbit slowly, like dancers long after the music has faded. And yet, in their stillness, they are poetic. Not because they dazzle, but because they endure. Because they represent a side of the universe we rarely see, the introverted cosmos, the one that doesn't shout but murmurs, the one that hides its most massive truths in shadow. Malin 1 is a poem written in gravity. A galaxy of ghosts orbiting a phantom halo. A monument not to light, but to mass, the invisible scaffolding that holds the cosmos together. It is a reminder that for all our telescopes and technology, the greatest wonders may still lie hidden. Not because we aren't looking, but because we're only now learning how to see. So when we gaze into the night, maybe we should listen as well as look. For there are stories told not in photons, but in silences, the cosmic ghost stories of Malin 1 and others like it. They drift between the galaxies, unseen but not absent. Lost, but not forgotten. Malin 1 stands as a silent testament to the cosmos' power to astonish not with brilliance, but with subtlety. In an age when astronomy is often drawn to the spectacular, the radiant quasars, the bursting supernovae, the swirling arms of luminous spirals, Malin 1 reminds us that some of the universe's greatest wonders whisper rather than roar. It is easy to overlook what cannot be easily seen. For centuries, astronomers catalogued the sky with light as their only guide, tracing the universe through glowing trails across the darkness. But Malin 1 was never meant to shine that way. It is not a beacon. It is a shadow the size of a galaxy, a footprint on the dark ocean of space left by a colossus that walks slowly and leaves no splash. And yet, despite its ghost-like presence, Malin 1 is monumental. Its disk extends over 650,000 light-years, more than 6 times the diameter of the Milky Way. It is not just large, it is unimaginably vast. It contains enough hydrogen to fuel millions of stars, and its gravity tugs on space with the quiet authority of an enormous dark matter halo. Its spiral arms are faint, stretched thin like whispers across the void. But they are there, resilient, ancient, persistent, marking time in slow cosmic revolutions. To see Malin 1 is not merely to look upon a distant galaxy. It is to confront the limits of our understanding, to recognize the quiet power of what lies just beyond our grasp. It invites us to widen our vision, to deepen our patience, to attune our instruments and our imagination not just to the spectacular, but to the invisible. This galaxy changed astronomy, not with noise or fire, but with absence. It forced astronomers to reconsider how galaxies form, where dark matter hides, and what kinds of structures might still be awaiting discovery in the black between the stars. It showed us that the universe is not empty where it is dark, only veiled. Malin 1 is a reminder that even in the most remote and silent corners of the universe, grandeur abides. That a galaxy can be enormous and powerful, and yet leave only the faintest trace of itself behind. That the cosmos is a place not just of light and life, but of long silences, mysterious, vast, and deeply beautiful. And perhaps that is Malin 1's greatest gift, not just the challenge it poses to our instruments, or the secrets it keeps in its gas and dust, but the lesson it teaches us, that the universe is more than what we see. That sometimes, the most magnificent colossus is the one that hides in the shadows, waiting patiently to be known. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.